The speed of light is one of the fundamental constants in physics. It travels at approximately 299,792 kilometers per second in a vacuum. This speed is often rounded to 300,000 kilometers per second for simplicity. Light speed sets a universal speed limit for how fast information and matter can travel. It plays a crucial role in the theory of relativity and our understanding of space and time. Light's behavior and speed are key to many scientific phenomena. In a vacuum, light speed remains constant, unaffected by the motion of the source or the observer. This constancy is a cornerstone of Einstein's theory of relativity. This change in speed is due to the light interacting with the atoms in the medium. Despite this slowing down, the fundamental speed limit set by light in a vacuum remains unchanged. The speed of light also affects time itself. As objects approach the speed of light, time slows down for them relative to an outside observer. This phenomenon, known as time dilation, is a key aspect of special relativity. Einstein's famous equation, E=mc2, shows the relationship between mass and energy, with the speed of light as a critical factor. This equation implies that as objects gain energy, their mass increases, making it harder to accelerate them to light speed. Reaching or exceeding light speed requires infinite energy, according to current physical laws. The implications of light speed are not just theoretical but also practical. GPS satellites, for instance, need to account for relativistic effects due to their high speeds and the Earth's gravitational field. Without these corrections, GPS accuracy would be significantly reduced. In astronomical observations, the speed of light allows us to see objects as they were in the past. Light from distant stars and galaxies takes millions or even billions of years to reach us. This means we are looking back in time when we observe these celestial bodies. Light speed is also crucial in understanding the vastness of the universe. Distances in space are often measured in light years, the distance light travels in 1 year. This measurement helps us comprehend the immense scales involved in cosmic distances. The speed of light forms the basis for many technologies, including lasers, fiber optics, and even the internet. These technologies rely on our understanding of light's properties and behavior. Advances in these fields continue to drive innovation and connectivity. In theoretical physics, light speed challenges our understanding of faster-than-light travel. Concepts like wormholes, warp drives, and quantum tunneling explore ways to bypass the light speed limit. Each theory offers intriguing possibilities and significant challenges. Experimental physics continually test the limits of our understanding of light speed. High-energy particle accelerators and advanced observational techniques probe the boundaries of relativity and quantum mechanics. These experiments seek to uncover new phenomena and validate existing theories. Cosmic phenomena, such as black holes and neutron stars, further illustrate the importance of light speed. The intense gravitational fields around these objects bend light and affect its speed. Studying these effects helps us understand extreme conditions in the universe. Einstein's theories transformed our understanding of light and its speed, reshaping modern physics. They provided a framework for unifying space, time, and energy. This framework continues to guide research and discovery. Despite its constancy, light speed's impact varies with context. In everyday life, we rarely notice relativistic effects. However, in high-speed or high-gravity environments, these effects become significant. Understanding them is crucial for advancing technology and exploring the universe. Faster-than-light travel holds immense importance for the future of space exploration. It represents the possibility of reaching distant stars and galaxies within human lifetimes. This could open up new frontiers for humanity, allowing us to explore and potentially colonize other worlds. One of the key motivations for faster-than-light travel is the vast distances in space. Even the nearest star, Proxima Centauri, is over 4 light-years away. At current spacecraft speeds, it would take tens of thousands of years to reach it. Faster-than-light travel could reduce this journey to mere years, or even months. Exploring other star systems could lead to the discovery of new planets. Some of these planets might be habitable or have resources that are scarce on Earth. This could provide new opportunities for scientific research, resource extraction, and even new homes for future generations. Faster-than-light travel could revolutionize our understanding of the universe. It would allow us to observe celestial phenomena up close and in real time. This could lead to breakthroughs in astrophysics, cosmology, and our understanding of the fundamental laws of nature. Interstellar travel could also play a crucial role in the survival of humanity. Earth faces numerous threats, both natural and man-made. Establishing colonies on other planets could act as a safeguard against potential global catastrophes. The technological advancements required for faster-than-light travel would have far-reaching impacts. Developing the necessary propulsion systems, energy sources and materials could lead to innovations that benefit many other fields. These advancements could improve our daily lives in ways we can't yet imagine. Such travel could enhance international collaboration. Space agencies and governments around the world would likely need to work together to achieve this goal. This could foster a sense of global unity and shared purpose, promoting peace and cooperation. The pursuit of faster-than-light travel could inspire a new generation of scientists, engineers, and explorers. The excitement and challenge of such a monumental task could attract bright minds to STEM fields. This influx of talent could drive further innovation and discovery. Economic opportunities would also emerge from faster-than-light travel. New industries could develop around space tourism, mining, and transportation. This could lead to economic growth and the creation of new jobs, both on Earth and in space. Such advancements could transform our culture and worldview. The ability to travel to distant stars might change how we see ourselves and our place in the universe. It could foster a sense of adventure and curiosity, pushing the boundaries of human potential. Scientific research would benefit from the ability to conduct experiments in diverse environments. Different planets and star systems offer unique conditions for studying physics, biology, and other sciences. This could lead to new discoveries and a deeper understanding of our universe. The quest for faster-than-light travel could also drive improvements in sustainability. Developing efficient energy sources and propulsion methods for space travel could have applications on Earth. This could help address environmental challenges and promote sustainable living. Ethical considerations would become increasingly important. As we venture into the cosmos, we would need to consider the impact of our actions on other worlds and potential life forms. This could lead to the development of new ethical frameworks and policies. Public interest in space and science would likely grow. The prospect of traveling to other stars could captivate the public imagination. This increased interest could lead to greater support for scientific research and space exploration initiatives. Ultimately, faster-than-light travel could redefine what it means to be human. It would push the limits of our technology, our knowledge, and our courage. The journey to achieve this capability could unite humanity in a common goal and expand our horizons beyond the confines of our planet. Faster-than-light travel is often misunderstood in popular culture. Many people think it's as simple as going faster than a certain speed, but the reality is far more complex. There's more to it than just surpassing the speed of light. A common misconception is that faster-than-light travel would allow instant travel to any point in the universe. While it could drastically reduce travel time, the distances involved are still immense. Even at superluminal speeds, journeys could take years or decades. Some believe that faster-than-light travel would violate the laws of physics. However, many theoretical models propose ways to achieve it without breaking these laws. These models often involve bending or warping space-time, rather than exceeding the speed of light directly. Many assume that faster-than-light travel is just around the corner. The truth is, we are still in the early stages of understanding the necessary physics. Practical faster-than-light travel, if possible, could be many centuries away. There's a misconception that we already have the technology to achieve faster-than-light travel. While science fiction often depicts advanced spaceships, our current technology is far from achieving this. Significant breakthroughs in physics and engineering are still needed. People often confuse faster-than-light travel with time travel. While they are related concepts in theoretical physics, they are not the same. Faster-than-light travel could have time dilation effects, but it does not inherently allow backward time travel. Many think that faster-than-light travel would be smooth and easy. In reality, it would involve navigating complex and potentially dangerous regions of space-time. The journey could be fraught with challenges and hazards we can't yet predict. Some believe that faster-than-light travel would solve all our space exploration problems. While it would be a huge leap forward, other challenges like radiation, life support, and human psychology would still need to be addressed. It's a step, not a complete solution. There's a notion that any civilization with faster-than-light travel would be invincible. However, such capabilities would come with their own set of vulnerabilities and limitations. Advanced technology does not equate to invulnerability. People often think that faster-than-light travel is purely a matter of speed. In fact, it involves complex concepts like space-time manipulation and energy fields. The science behind it is much more intricate than just going fast. Many assume that faster-than-light travel would be instantaneous communication as well. However, the principles governing travel and communication are different. Faster-than-light communication is a separate challenge with its own set of difficulties. Some believe that once we achieve faster-than-light travel, it will be universally accessible. In reality, it would likely be restricted to those with significant resources and technology. It could remain the domain of governments and large organizations for a long time. There's a misconception that faster-than-light travel would be free from relativistic effects. Even if we bypass the speed of light, relativity still governs the behavior of objects in space-time. Time dilation and other effects would still play a role. Many think that achieving faster-than-light travel would end all need for slower space travel. In truth, sublight speed travel would still be important for shorter distances and certain missions. Both types of travel would likely coexist and complement each other. Finally, there's the belief that faster-than-light travel would be simple to control and navigate. The reality is that it would require incredibly precise calculations and control mechanisms. The complexities of space-time would make navigation a significant challenge. The objective of this video is to explore the fascinating world of faster-than-light travel. We'll delve into the various theories and concepts that scientists have proposed over the years. Understanding these ideas will help us grasp the potential and challenges of surpassing the speed of light. We aim to provide a comprehensive overview of the most prominent theories. Each theory will be examined in detail, highlighting its strengths and weaknesses. This will give you a clear understanding of where current research stands. By the end of this video, you'll have a solid grasp of the scientific principles involved. We'll break down complex ideas into manageable, easy-to-understand segments. This approach ensures that everyone, regardless of their background, can follow along. We'll explore how these theories could revolutionize space travel. Faster-than-light travel could open up new possibilities for exploration and colonization. We'll discuss the potential impact on humanity's future in space. Another key objective is to address common misconceptions. Many people have ideas about faster-than-light travel that are based on science fiction rather than science fact. We'll separate myth from reality. We'll also highlight the current state of research in this field. Understanding where we are now helps set realistic expectations for the future. You'll learn about ongoing experiments and theoretical work that are pushing the boundaries of our knowledge. Our goal is to inspire curiosity and wonder about the universe. The idea of traveling faster than light captures the imagination. We hope to fuel your interest in space and the possibilities that lie beyond our current reach. We'll look at the technological advancements needed to achieve these goals. What kind of propulsion systems, energy sources, and materials might be required? This discussion will show the practical challenges and innovations involved. Another important aspect is the ethical and philosophical implications. What would faster-than-light travel mean for humanity? We'll explore the broader consequences of potentially achieving such a monumental feat. We'll provide historical context for these theories. Many ideas have evolved over decades or even centuries. Understanding their development helps appreciate the progress made and the obstacles still ahead. The video will also showcase the pioneers in this field. Who are the key scientists and thinkers who have contributed to our understanding? Highlighting their work and achievements will give credit to those pushing the boundaries. We aim to stimulate discussion and debate. Faster-than-light travel is a topic with many perspectives and opinions. Encouraging viewers to think critically and engage with the content is a primary goal. Our content is designed to be educational yet engaging. We'll use visual aids, animations, and analogies to make complex concepts accessible. This approach ensures that learning about these theories is enjoyable and informative. We'll also touch on the speculative and imaginative aspects of this topic. While grounded in science, some ideas push the limits of what we currently know. Exploring these possibilities can be both fun and thought-provoking. Finally, we aim to provide a balanced view. While faster-than-light travel is an exciting prospect, it's essential to understand the challenges and limitations. Presenting a well-rounded perspective ensures a realistic understanding of the topic. First, we'll start with an introduction to the concept of faster-than-light travel. This will include a brief overview of the speed of light and its significance in physics. Setting the stage with basic concepts will help us build a foundation for more complex theories. Next, we'll dive into Einstein's theory of relativity. We'll explain how this theory sets the speed of light as a cosmic speed limit. This section will also cover time dilation and the energy requirements for reaching light speed. After that, we'll explore the concept of wormholes. We'll discuss what wormholes are, how they might enable faster travel, and the theoretical and practical challenges involved. This section will highlight both the potential and the risks. Following wormholes, we'll look at warp drives, specifically the Alcubierre drive. We'll explain how space-time manipulation could allow faster-than-light travel. This part will cover the science behind warp bubbles and the exotic matter required. Then we'll move on to tachyons, hypothetical particles that travel faster than light. We'll delve into the properties of tachyons, their theoretical implications, and the challenges of detecting and utilizing them. This section will explore the intriguing possibilities they present. Quantum tunneling will be our next topic. We'll explain the basics of quantum mechanics and how particles can tunnel through barriers. This section will discuss the implications for faster-than-light travel and the experimental evidence supporting these ideas. We'll then shift our focus to cosmic strings. These theoretical objects could facilitate faster-than-light travel by creating shortcuts through space-time. We'll discuss their properties, potential energy sources, and the current state of research in this area. The next section will cover dark energy and the expansion of space. We'll explore how the accelerating expansion of the universe could be harnessed for faster travel. This part will delve into the theoretical models and the energy requirements involved. After discussing dark energy, we'll examine the role of negative mass and exotic matter. These concepts are crucial for many faster-than-light travel theories. We'll explain their properties, how they might be created, and the challenges they present. We'll then look at faster-than-light communication, focusing on quantum entanglement. We'll discuss how entanglement could allow instantaneous information transfer and the challenges in harnessing this phenomenon. This section will highlight the potential for revolutionizing communication. Next, we'll cover real-world projects like Breakthrough Starshot. We'll provide an overview of the initiative, its objectives, and the technologies being developed. This section will showcase the practical efforts towards achieving faster-than-light travel. We'll then explore other related projects and initiatives around the world. Highlighting various efforts will provide a broader perspective on the global pursuit of faster-than-light travel. This part will also discuss potential future developments and timelines. Following the project discussions, we'll address the broader implications of achieving faster-than-light travel. This includes the potential impact on space exploration, colonization, and our understanding of the universe. We'll also touch on the societal and ethical considerations. Our final main section will be a recap of the key theories and concepts we've covered. This will help reinforce understanding and provide a summary of the most important points. This recap will ensure that all viewers are on the same page before we conclude. Throughout the presentation, we'll use visual aids, animations, and analogies to make the complex concepts more accessible. This approach will help engage viewers and ensure that the material is both informative and enjoyable to learn. Special relativity, introduced by Albert Einstein in 1905, fundamentally changed our understanding of space and time. At its core, it postulates that the laws of physics are the same for all non-accelerating observers. This principle leads to some surprising and non-intuitive results. One of the most famous aspects of special relativity is the constancy of the speed of light. Regardless of the motion of the source or the observer, the speed of light in a vacuum remains constant. This constancy is a cornerstone of the theory. Special relativity also introduces the concept of time dilation. As an object approaches the speed of light, time for that object slows down relative to an observer at rest. This means that a high-speed traveler would age more slowly than someone stationary. Another key concept is length contraction. Objects moving close to the speed of light will appear shortened in the direction of motion when observed from a stationary frame of reference. This effect is only noticeable at extremely high speeds. The theory also redefines our understanding of simultaneity. Events that appear simultaneous in one frame of reference may not be simultaneous in another. This relativity of simultaneity highlights the interconnected nature of space and time. Special relativity combines space and time into a single four-dimensional continuum known as space-time. In this framework, time is treated as a dimension similar to the three spatial dimensions. This unification is crucial for understanding relativistic effects. The famous equation E=mc2 emerges from special relativity. It shows that mass and energy are equivalent, implying that a small amount of mass can be converted into a large amount of energy. This principle underlies the energy produced by nuclear reactions. Special relativity also affects momentum and energy. As an object's speed increases, its momentum and kinetic energy grow in ways that differ from classical mechanics. At speeds close to the speed of light, these quantities increase dramatically. The theory has been confirmed by numerous experiments. Observations of particles moving at high velocities, such as those in particle accelerators, consistently match the predictions of special relativity. This experimental validation underscores its accuracy. Special relativity impacts many aspects of modern technology. For example, the GPS system must account for relativistic effects to provide accurate positioning data. Without these corrections, the system would quickly become inaccurate. The theory also has implications for cosmology and our understanding of the universe. It plays a role in the dynamics of stars, black holes, and the expansion of the universe. Special relativity is a foundational element of modern astrophysics. In addition to its scientific impact, special relativity has philosophical implications. It challenges our intuitive notions of space and time, forcing us to rethink concepts that once seemed absolute. This shift has profound effects on our worldview. Special relativity laid the groundwork for Einstein's later work on general relativity. While special relativity deals with non-accelerating frames of reference, general relativity extends these principles to include gravity and acceleration. Understanding special relativity is essential for grasping more advanced theories in physics. It provides the basis for exploring phenomena at high velocities and under extreme conditions. Mastery of these concepts is crucial for physicists and engineers. Through its revolutionary principles, special relativity continues to influence and inspire scientific thought. Its legacy endures in the ongoing quest to understand the fundamental nature of reality, pushing the boundaries of human knowledge. The speed of light is considered the ultimate speed limit in the universe. According to Einstein's theory of relativity, nothing can travel faster than light in a vacuum. This limit is a fundamental aspect of the laws of physics. One reason for this limit is that as objects move faster, their mass effectively increases. As an object approaches the speed of light, its mass approaches infinity. This means it would require infinite energy to accelerate to light speed. Photons, the particles of light, have no rest mass, allowing them to travel at light speed. For anything with mass, reaching this speed is impossible due to the infinite energy requirement. This distinction is crucial for understanding why light holds this unique position. The speed of light also ensures causality in the universe. Causality means that cause precedes effect. If faster than light travel were possible, it could lead to violations of this principle, resulting in paradoxes where effects occur before their causes. In addition to preventing causality violations, the light speed limit preserves the structure of space-time. It ensures that the relationships between space and time remain consistent across different frames of reference. This consistency is a cornerstone of relativity. Relativity shows that the speed of light is the same in all inertial frames of reference. This invariance is independent of the motion of the light source or the observer. It's a unique property that sets light apart from other phenomena. The speed of light is not just a theoretical construct, but has practical implications. Technologies like radar, communications, and GPS rely on this constant speed. Understanding and utilizing this limit is essential for modern technology. Astronomical observations also depend on the speed of light. When we observe distant objects, we are seeing light that has traveled for millions or billions of years. This speed limit helps us understand the scale and history of the universe. The speed of light in a vacuum is approximately 299,592 kilometers per second. This exact value is crucial for precision in scientific calculations and measurements. It's a fundamental constant that underpins many areas of physics. In other media, such as water or glass, light slows down due to interactions with the material. However, even in these cases, the principle that nothing can exceed light speed in a vacuum remains intact. This distinction helps clarify the universality of the speed limit. Special relativity shows that traveling at or above light speed would result in infinite time dilation. Time would effectively stop for an object moving at light speed. This consequence further illustrates the impossibility of surpassing this cosmic limit. The speed of light also connects to energy and momentum. In relativistic physics, these quantities behave differently at high speeds. The light speed limit ensures that energy and momentum remain finite and calculable. In the search for faster-than-light travel, many theories propose bending or warping space-time. These ideas aim to circumvent the light speed limit, without directly exceeding it. They highlight the creative approaches scientists are exploring. Understanding the speed of light helps us grasp the vastness of space. Even traveling at light speed, it would take years to reach the nearest stars. This perspective emphasizes the immense scales involved in interstellar distances. The speed of light as a cosmic speed limit remains one of the most intriguing aspects of modern physics. It shapes our understanding of the universe, guides technological advancements, and inspires ongoing scientific exploration. Time dilation is one of the most fascinating consequences of special relativity. It describes how time slows down for an object moving close to the speed of light. This effect becomes significant at velocities approaching light speed. Imagine traveling in a spaceship at near light speed. To an outside observer, your clock would tick slower compared to someone at rest. This means you would age more slowly during your journey. This phenomenon is called time dilation. The effects of time dilation have been confirmed through experiments. For example, particles moving at high speeds in particle accelerators decay more slowly than those at rest. These observations align with the predictions of special relativity. Astronauts experience a very slight time dilation effect due to their high speeds in orbit. While the effect is minuscule, it is measurable. This real-world example illustrates how time dilation impacts even human space travel. Time dilation also affects GPS satellites. The high speeds and weaker gravity in orbit cause their clocks to run faster than those on Earth. Corrections are necessary to ensure accurate positioning data, demonstrating the practical importance of this effect. Length contraction is another intriguing result of special relativity. Objects moving at high speeds appear shortened in the direction of motion. This effect, like time dilation, becomes noticeable only at speeds close to light. Consider a spaceship traveling near light speed. To an outside observer, the spaceship would appear compressed along its direction of travel. This phenomenon is known as length contraction. The amount of contraction depends on the object's speed. The faster the object moves, the greater the contraction. At light speed, the object's length would theoretically contract to zero, illustrating the extremity of relativistic effects. Length contraction has implications for our understanding of space and distance. It shows that measurements of space are relative, depending on the observer's frame of reference. This relativity challenges our intuitive notions of fixed distances. Experiments with fast-moving particles have confirmed length contraction. For example, muons created in the upper atmosphere travel further than expected before decaying. Their high speed causes length contraction, allowing them to reach the Earth's surface. Both time dilation and length contraction are interconnected aspects of special relativity. They arise from the same underlying principles that govern the behavior of space and time. Understanding one helps illuminate the other. These effects challenge our everyday experiences. At typical speeds, time and length appear constant and absolute. Relativistic speeds reveal the fluid and dynamic nature of these dimensions, fundamentally altering our perception. Time dilation and length contraction are crucial for advanced physics and cosmology. They provide insights into the behavior of objects under extreme conditions, such as near black holes or in high-energy particle collisions. The study of these effects continues to push the boundaries of science. Researchers explore their implications for new technologies and our understanding of the universe. Time dilation and length contraction remain central topics in theoretical and experimental physics. These relativistic effects not only deepen our understanding of the cosmos, but also inspire new generations of scientists. The strange and counterintuitive nature of time dilation and length contraction captures the imagination, driving curiosity and discovery in the field of physics. Reaching the speed of light requires enormous amounts of energy. According to Einstein's theory of relativity, as an object accelerates, its mass effectively increases. This increase in mass makes it progressively harder to continue accelerating the object. The closer an object gets to the speed of light, the more energy is needed to increase its speed. This relationship is not linear. The energy required grows exponentially. At light speed, the required energy becomes infinite, making it practically impossible with our current understanding of physics. For an object with mass, no matter how small, achieving light speed means overcoming this exponential energy demand. Even particles accelerated in our most advanced particle accelerators, like those at CERN, require massive amounts of energy to approach light speed but never actually reach it. The concept of infinite energy is a significant barrier. Our current technologies and energy sources are nowhere near capable of providing the levels needed. This limitation holds true for any conceivable propulsion system based on known physics. In particle accelerators, we see the practical implications of these energy requirements. Protons, for example, can be accelerated to over 99.9999% of the speed of light, but doing so requires enormous amounts of power and highly specialized equipment. To conceptualize the energy needed, consider a simple object like a spacecraft. As the spacecraft accelerates towards light speed, its kinetic energy increases dramatically. The energy input required grows so vast that even the total energy output of a star would be insufficient. Even theoretical propulsion methods, such as antimatter engines, face this energy hurdle. While antimatter reactions provide high energy outputs, they still fall short of the infinite energy required to reach light speed. This underscores the magnitude of the challenge. Energy efficiency becomes a critical factor in these discussions. Current propulsion methods, whether chemical rockets or ion drives, are far too inefficient for the task. New, groundbreaking advances in physics and engineering are necessary to even approach feasible energy requirements. Some theories propose alternative approaches, such as using warp drives or manipulating space-time itself. These methods aim to circumvent the need for infinite energy by altering the fundamental properties of space and time, rather than directly accelerating a mass to light speed. The concept of a warp drive, for example, involves creating a bubble of space-time that moves faster than light. Within this bubble, the spacecraft would remain stationary relative to its local space-time. This approach sidesteps the infinite energy problem by leveraging the malleability of space-time. However, even these advanced concepts face significant energy demands. Creating and sustaining a warp bubble would require exotic forms of energy and matter that we currently do not have. Theoretical models often involve energy scales far beyond what is presently achievable. Exploring these energy requirements pushes the boundaries of theoretical physics. It challenges our understanding of energy, mass, and the nature of the universe. Researchers continue to explore these frontiers, seeking potential breakthroughs that could one day make faster-than-light travel possible. In addition to the theoretical challenges, practical considerations also come into play. Generating, storing, and efficiently using such vast amounts of energy pose engineering problems of unprecedented scale. Overcoming these obstacles is as crucial as the theoretical breakthroughs themselves. The quest to reach or exceed light speed drives innovation across multiple scientific disciplines. From advances in energy production and storage to new materials and propulsion methods, each step forward brings us closer to overcoming the immense energy barriers. Understanding the energy requirements for light-speed travel not only illuminates the challenges, but also inspires the pursuit of new solutions. It reminds us of the vast potential and the profound mysteries that remain in the realm of high-speed space travel. Faster-than-light travel carries profound implications for our understanding of the universe. If achieved, it would revolutionize space exploration, allowing us to reach distant stars and galaxies in a fraction of the time currently possible. This breakthrough could open up new frontiers for human expansion and discovery. The ability to travel faster than light would challenge our current laws of physics. It would force a re-evaluation of the principles that have governed our understanding of space and time for over a century. This could lead to new, groundbreaking theories and a deeper comprehension of the cosmos. Exploring the implications for causality is crucial. Faster-than-light travel raises the possibility of time travel, with events potentially occurring out of sequence. This could result in paradoxes that defy our conventional notions of cause and effect, posing significant philosophical and scientific challenges. Communication across vast distances would be transformed. Messages could be sent instantaneously across the universe, enabling real-time communication between Earth and distant space colonies. This would have a dramatic impact on the way we interact and coordinate across space. The discovery of extraterrestrial life could become more feasible. Faster-than-light travel would allow us to visit exoplanets that are currently beyond our reach. This exploration could lead to the detection of life forms and entirely new ecosystems, profoundly altering our place in the universe. The potential for faster-than-light travel would also impact international relations and space policy. The strategic advantages of such technology could lead to new forms of competition and collaboration among nations. It would necessitate the development of new treaties and regulatory frameworks. From an economic perspective, the ability to travel faster than light could spur the development of new industries. Space mining, tourism, and colonization could become viable sectors, creating economic growth and new opportunities for investment and employment. Faster-than-light travel could also change our understanding of energy and propulsion. The technologies developed to achieve such speeds would likely have applications beyond space travel, leading to innovations in energy production, transportation, and other fields. The implications for human psychology and society are significant. Living and traveling in space at such speeds would require new adaptations and cultural shifts. The experience of time and distance would change, potentially altering our perception of reality and our place in the universe. The environmental impact of faster-than-light travel must also be considered. The energy requirements and potential side effects of such travel could have unforeseen consequences. Responsible development and management of this technology would be essential to mitigate any negative impacts. In terms of scientific research, faster-than-light travel would enable unprecedented opportunities. Scientists could study phenomena up close that are currently only observable from great distances. This would lead to a wealth of new data and insights about the universe. The potential for exploration and colonization of other star systems could ensure the long-term survival of humanity. Establishing colonies on other planets would provide a safeguard against existential threats to life on Earth, such as asteroid impacts or global catastrophes. Cultural and philosophical perspectives on our place in the universe would evolve. The ability to traverse the cosmos at such speeds would inspire new forms of art, literature, and philosophy. It would challenge and expand our collective imagination and sense of identity. The ethical considerations of faster-than-light travel are profound. Issues such as the impact on indigenous life forms, the use of vast amounts of energy, and the potential for inequality in access to this technology would need to be carefully addressed. Ultimately, the implications of faster-than-light travel extend far beyond the realm of science and technology. They touch on every aspect of human existence, from our understanding of the universe to our societal structures and ethical frameworks. Exploring these implications is essential as we continue to push the boundaries of what is possible. Faster-than-light travel refers to the concept of traveling at speeds exceeding the speed of light in a vacuum, which is approximately 299,792 kilometers per second. This idea is a staple of science fiction, but it also has roots in theoretical physics. The concept challenges our current understanding of physics, particularly Einstein's theory of relativity. According to relativity, as an object approaches the speed of light, its mass increases exponentially, requiring infinite energy to reach light speed. This makes faster-than-light travel seem impossible with conventional means. Despite this, various theories and concepts have been proposed to circumvent the light-speed barrier. These ideas often involve bending or manipulating space-time itself, rather than directly accelerating an object to light speed. One such concept is the idea of wormholes. Wormholes are hypothetical passages through space-time that could create shortcuts between distant points in the universe. If traversable, they could allow for faster-than-light travel by effectively reducing the distance traveled. Another popular theoretical framework is the Alcubierre warp drive. Proposed by physicist Miguel Alcubierre, this concept involves creating a warp bubble that contracts space in front of a spacecraft and expands it behind. Within this bubble, the spacecraft would remain stationary, bypassing the need to travel faster than light itself. Tachyons are another fascinating theoretical idea. These hypothetical particles always move faster than light. While their existence has not been confirmed, they offer intriguing possibilities for understanding faster-than-light phenomena. Quantum tunneling is a phenomenon in quantum mechanics, where particles can pass through energy barriers instantaneously. While not directly related to faster-than-light travel, it suggests that certain quantum effects might be harnessed for superluminal transport. Cosmic strings, theoretical one-dimensional defects in the fabric of spacetime, are another concept. If they exist, they could potentially create conditions that allow for faster-than-light travel by warping spacetime around them. Dark energy and the accelerated expansion of the universe present another avenue of exploration. Some theories suggest that by harnessing or mimicking these cosmic forces, it might be possible to achieve faster-than-light travel. Negative mass and exotic matter also play roles in these theories. Negative mass, if it exists, could produce repulsive gravitational effects necessary for phenomena like the Alcubierre warp drive, providing the exotic energy needed to warp space-time. Faster-than-light communication involves the concept of transmitting information instantaneously. Quantum entanglement, where particles become interconnected regardless of distance, offers a potential mechanism for this, though it does not violate relativity in the same way as physical travel. Breakthrough Starshot is an example of a real-world project pushing the boundaries of high-speed space travel. While it aims for relativistic speeds rather than faster-than-light travel, it represents the cutting edge of our current technological capabilities. Theoretical physicists continue to explore these ideas, pushing the boundaries of our understanding of space, time, and energy. Each concept, while speculative, offers insights into the potential for faster-than-light travel. These theories often require forms of matter and energy that we currently cannot produce or control. The search for exotic matter and the means to manipulate space-time continues to drive theoretical and experimental physics. Understanding the theoretical background of faster-than-light travel helps us appreciate the challenges and possibilities. It also fuels the imagination, inspiring scientists and the public alike to envision what might one day be possible. Einstein-Rosen bridges, commonly known as wormholes, are theoretical passages through space-time. They were first proposed by Albert Einstein and Nathan Rosen in 1935 as part of their work on general relativity. A wormhole can be visualized as a tunnel connecting two distant points in space-time. This tunnel could theoretically allow for instant travel between these points, bypassing the intervening space. Wormholes are solutions to the equations of general relativity. They describe a bridge between two black holes, or other significant gravitational wells. In theory, if such a bridge could be stabilized, it could provide a shortcut through space-time. The mouth of a wormhole would be a spherical entrance, possibly surrounded by intense gravitational forces. Traveling through this mouth would lead to the other side of the bridge, potentially many light years away. One of the main challenges with wormholes is their stability. According to theoretical models, they would require exotic matter with negative energy density to remain open. Without such matter, a wormhole would collapse too quickly for anything to traverse it. Exotic matter, which has not yet been discovered, would have unusual properties. It would be capable of producing the negative energy necessary to counteract the wormhole's natural tendency to close. Finding or creating such matter is a significant hurdle. Wormholes could theoretically allow for both faster-than-light travel and time travel. If one mouth of the wormhole is accelerated to near-light speed or placed in a strong gravitational field, time dilation could occur. This could create a time difference between the two ends. The concept of traversable wormholes has been popularized in science fiction. Movies and books often depict them as gateways to other worlds or dimensions, capturing the imagination of audiences. These fictional portrayals often gloss over the complex physics involved. In reality, traversing a wormhole would likely involve extreme gravitational forces. These forces could pose significant dangers to travelers, potentially stretching and compressing them in what is known as spaghettification. Research into quantum gravity might provide further insights into wormholes. Theoretical frameworks like string theory and loop quantum gravity aim to reconcile general relativity with quantum mechanics, potentially offering new understandings of wormholes. Experimental evidence for wormholes is currently lacking. Detecting them would require observing effects that cannot be explained by other phenomena. This search continues to be a major area of interest in both theoretical and observational astrophysics. If wormholes could be stabilized and traversed, they would revolutionize space travel. They would make it possible to reach distant galaxies in a fraction of the time it would take using conventional propulsion methods. This breakthrough could expand our reach across the universe. The study of wormholes also has implications for understanding the fundamental nature of reality. It challenges our concepts of space, time, and causality, prompting new questions about the structure of the universe. Despite the challenges, the idea of wormholes continues to inspire scientists. It pushes the boundaries of theoretical physics and encourages innovative thinking about the possibilities of space travel. Einstein-Rosen bridges remain a tantalizing possibility in our quest to explore the cosmos. They represent the intersection of science fiction and scientific inquiry, driving both our imaginations and our research into the unknown. Wormholes could serve as shortcuts through the fabric of space-time, enabling travel between distant points in the universe far more quickly than conventional travel methods. By bending space-time, a wormhole could effectively reduce the distance between two locations, allowing a spacecraft to traverse vast cosmic distances in a shorter time. The concept of a wormhole hinges on the idea that space-time can be curved or warped by massive objects. If space-time can be manipulated to create a tunnel-like structure, it could connect two separate regions of space, providing a direct path that bypasses the intervening space. For a wormhole to enable faster travel, it must remain stable and traversable. This requires the presence of exotic matter with negative energy density to keep the tunnel open. Such matter would counteract the natural tendency of the wormhole to collapse, creating a stable passageway. A traversable wormhole would have two ends, or mouths, connected by a throat. The distance through the throat could be much shorter than the distance between the mouths in normal space. Entering one mouth would allow instant travel to the other, regardless of the distance in the external universe. Theoretical models suggest that if one end of a wormhole is placed near a massive object, such as a black hole, or accelerated to near light speed, time dilation effects could occur. This could allow for not only faster travel but also potential time travel, as time would pass differently at each end of the wormhole. Traveling through a wormhole would require precise navigation to avoid the intense gravitational forces near the mouths. Advanced shielding and propulsion systems would be necessary to protect the spacecraft and its occupants from these extreme conditions. The potential for wormholes to enable interstellar travel is profound. With a stable wormhole, a journey that would take thousands of years using conventional propulsion could be completed in a fraction of the time. This could make colonization of distant star systems feasible within a human lifetime. In addition to interstellar travel, wormholes could facilitate instantaneous communication across vast distances. Messages sent through a wormhole could reach their destination without the time delay associated with light-speed transmission, revolutionizing our ability to communicate across the cosmos. The energy requirements for creating and sustaining a wormhole are enormous. Theoretical calculations suggest that it would require energy on a scale comparable to the output of entire stars. Harnessing such energy would necessitate advances in energy production and storage far beyond our current capabilities. Despite the challenges, the potential benefits of wormhole travel drive ongoing research in theoretical physics. Scientists are exploring various models and mathematical frameworks to better understand how wormholes could be realized and utilized for practical travel. If wormholes can be engineered, they could provide a solution to the vast distances that currently limit our exploration of the universe. By reducing travel times, we could explore new worlds, study distant phenomena up close, and potentially encounter extraterrestrial civilizations. The implications for science and technology are vast. Wormhole travel would open up new avenues for scientific research, allowing us to conduct experiments and observations in parts of the universe that are currently inaccessible. From a philosophical perspective, wormhole travel challenges our understanding of space, time, and causality. It raises questions about the nature of reality and our place in the universe, prompting new theories and ideas about the fundamental structure of existence. The pursuit of wormhole technology embodies humanity's enduring quest to push the boundaries of what is possible. It represents the intersection of science fiction and scientific inquiry, driving us to explore the farthest reaches of our imagination and our universe. While the realization of wormhole travel remains speculative, the theoretical groundwork laid by physicists provides a foundation for future breakthroughs. Continued research and innovation may one day turn the dream of faster-than-light travel into reality, transforming our capabilities and our understanding of the cosmos. One major challenge of using wormholes for travel is stability. Wormholes are inherently unstable and could collapse before anything can pass through them. Keeping a wormhole open long enough for travel would require exotic matter with negative energy density. Another significant risk involves the immense gravitational forces near a wormhole's entrance. These forces could stretch and compress objects, a process known as spaghettification. This intense gravity poses a severe threat to anything attempting to travel through a wormhole. Finding or creating the exotic matter needed to stabilize a wormhole is currently beyond our technological capabilities. Exotic matter is hypothetical and has properties that are not observed in conventional matter. The absence of this material is a major barrier. Even if a stable wormhole could be created, navigating through it would be another challenge. The environment inside a wormhole could be unpredictable and hazardous. Ensuring safe passage through these conditions would require advanced technology and precise control. There is also the issue of wormhole mouths potentially being separated by vast distances. Aligning and synchronizing these entrances would be an enormous technical challenge, requiring precise measurements and control over astronomical scales. Energy requirements for creating and maintaining a wormhole are another significant hurdle. The amount of energy needed to open a wormhole could be astronomical, far beyond what we can currently produce. This limitation poses a fundamental barrier to practical use. Theoretical models suggest that wormholes could lead to time travel, which brings its own set of paradoxes and risks. Traveling back in time could create causality violations, leading to scenarios where cause and effect are reversed. These paradoxes could have unpredictable and potentially dangerous consequences. Radiation exposure is another concern. The high-energy environment near a wormhole could produce intense radiation. This radiation could harm or destroy any travelers or equipment passing through, necessitating robust shielding and protection mechanisms. There is also the potential for encountering unknown physical phenomena. Wormholes, if they exist, could connect to different regions of space-time with unfamiliar physical laws and conditions. These unknowns add another layer of risk to wormhole travel. Security risks are another consideration. If wormholes allow for near-instantaneous travel across vast distances, they could be exploited for malicious purposes. Ensuring the security and control of wormhole travel would be crucial to prevent misuse. The effects of entering and exiting a wormhole on human physiology are not understood. The extreme conditions within a wormhole could have unknown impacts on the human body. Research into these effects would be essential before any manned missions could be considered. Wormholes could also present legal and ethical challenges. The ability to traverse vast distances quickly could lead to conflicts over territory and resources in space. International agreements and regulations would be necessary to manage these new dynamics. Environmental impacts on both ends of a wormhole must also be considered. The creation and maintenance of a wormhole could disrupt local space-time and have unintended consequences for nearby systems. Understanding these impacts would be crucial for responsible use. The theoretical nature of wormholes means there is still much we do not know. Our current understanding is based on mathematical models and simulations. Real-world experimentation and observation are needed to validate these theories and understand their practical implications. Despite these challenges and risks, the potential benefits of wormhole travel are immense. Overcoming these obstacles requires significant advancements in physics, engineering, and technology. Continued research and exploration will be key to unlocking the mysteries and possibilities of wormholes. Current scientific research on wormholes is primarily theoretical. Physicists use the equations of general relativity to explore the properties and potential of wormholes. These theoretical studies aim to understand the conditions under which wormholes could exist and be stable. Researchers are investigating the types of exotic matter required to keep a wormhole open. This exotic matter would need to have negative energy density, something not observed in the natural world. Theoretical physicists explore different models and possibilities for such materials. Quantum mechanics also plays a crucial role in wormhole research. Some theories suggest that quantum effects could help stabilize wormholes. This intersection of quantum mechanics and general relativity is a hotbed of research and could provide new insights. Advanced simulations and computational models are used to study wormholes. These tools allow scientists to explore how wormholes might form, behave, and interact with the surrounding space-time. Computational physics provides a virtual laboratory for these complex phenomena. Researchers are also examining the potential for naturally occurring wormholes in the universe. Observational astrophysics seeks evidence of such structures through anomalies in gravitational fields or unusual cosmic phenomena. However, no definitive evidence has been found so far. Theoretical work by physicists like Kip Thorne has advanced our understanding of wormholes. Thorne's work on traversable wormholes explores the conditions needed for safe passage through these structures. His research has been foundational in bridging theory with potential practicality. Another area of research is the connection between wormholes and black holes. Some theories suggest that wormholes could be linked to black holes or formed during their creation. Studying black holes could provide clues about the nature and existence of wormholes. Researchers are also interested in the role of wormholes in cosmology. If wormholes exist, they could provide shortcuts across the universe, influencing our understanding of cosmic structure and evolution. This could have profound implications for cosmology. Experimental physicists are looking for indirect evidence of wormholes. This includes searching for unusual gravitational effects or high-energy cosmic events that cannot be explained by current models. Such evidence could hint at the presence of wormholes. Interdisciplinary collaboration is key in wormhole research. Physicists, astronomers, and engineers work together to explore theoretical models and potential practical applications. This collaborative approach helps advance our understanding from multiple perspectives. Some researchers are exploring the potential for creating artificial wormholes. This highly speculative work involves advanced theoretical physics and futuristic technology concepts. The goal is to understand what it would take to construct a wormhole in a controlled environment. Wormhole research is also linked to the study of quantum gravity. Understanding how gravity works at quantum scales could provide insights into the nature of wormholes. This area of research aims to unify general relativity and quantum mechanics, offering a deeper understanding of the universe. The concept of wormholes also intersects with string theory. String theory proposes that fundamental particles are one-dimensional strings, and it predicts the existence of multiple dimensions. Wormholes could be a natural feature in such a multidimensional universe. Despite the theoretical nature of current research, it continues to push the boundaries of our understanding. Each new theoretical development or model brings us closer to understanding whether wormholes can exist and how they might be utilized. Ongoing research into wormholes represents the cutting edge of theoretical physics. While many questions remain unanswered, the pursuit of knowledge about these fascinating structures continues to inspire and drive scientific inquiry into the nature of the universe. The Alcubierre drive is a theoretical concept for faster-than-light travel proposed by physicist Miguel Alcubierre in 1994. It involves the idea of manipulating space-time to achieve superluminal speeds. The drive works by creating a warp bubble around a spacecraft. This bubble contracts space-time in front of the spacecraft and expands it behind. Within this bubble, the spacecraft would remain stationary, while the bubble itself moves through space. This method theoretically allows for faster-than-light travel without violating the laws of physics. Since the spacecraft itself isn't moving through space faster than light, it bypasses the relativistic speed limit. One of the key features of the Alcubierre drive is its reliance on exotic matter. This exotic matter would need to have negative energy density, something not yet discovered or understood. Negative energy is essential for creating and maintaining the warp bubble. The energy requirements for the Alcubierre drive are immense. Early calculations suggested that the drive would need more energy than the entire mass of the observable universe. However, subsequent refinements have reduced these requirements, though they remain astronomically high. The shape of the warp bubble is crucial. It must be asymmetrical to allow for forward motion. The front contracts space-time, while the rear expands it, propelling the bubble and the spacecraft forward. Inside the warp bubble, occupants would not experience acceleration. They would be in free fall, protected from the extreme forces typically associated with high-speed travel. This makes the Alcubierre drive theoretically safe for human passengers. The concept of the Alcubierre drive draws inspiration from science fiction, particularly the warp drives depicted in shows like Star Trek. While the science behind it is far more complex, the idea resonates with our imaginations. One of the challenges of the Alcubierre drive is controlling the warp bubble. Precise manipulation of spacetime would be required to navigate and steer the spacecraft. This level of control is beyond our current technological capabilities. Theoretical physicists are exploring ways to generate and sustain the negative energy needed for the drive. Concepts like Casimir effect, which creates negative energy between closely spaced plates, are being studied as potential sources. Another area of research involves minimizing the energy requirements. Some proposals suggest using configurations of multiple warp bubbles or altering the geometry of the bubble to reduce the energy needed. The Alcubierre drive, while speculative, has opened up new avenues of research in physics. It challenges our understanding of space-time and encourages innovative thinking about the possibilities of interstellar travel. Critics point out that even if the drive is theoretically possible, the practical challenges are immense. The creation, manipulation, and control of a warp bubble are tasks that may remain insurmountable for the foreseeable future. The study of the Alcubierre drive also has implications for understanding the nature of space-time itself. It pushes the boundaries of general relativity and quantum mechanics, offering insights into the fundamental workings of the universe. Despite the hurdles, the Alcubierre drive represents a fascinating intersection of science fiction and theoretical physics. It embodies the spirit of exploration and the relentless pursuit of knowledge that drives humanity's quest to reach the stars. Space-time manipulation is a fundamental concept behind the Alcubierre drive and other faster-than-light travel theories. It involves altering the fabric of space-time to achieve desired effects, such as faster travel. Warp bubbles are a specific form of space-time manipulation. These bubbles create a region of space-time that can move faster than the speed of light, relative to the space outside the bubble. The spacecraft inside the bubble remains in a local space-time frame, unaffected by relativistic effects. Creating a warp bubble requires the manipulation of space-time in a precise manner. The front of the bubble must contract space-time, while the back expands it. This creates a differential that propels the bubble forward. Exotic matter with negative energy density is crucial for forming and maintaining a warp bubble. This negative energy counteracts the positive energy that would naturally cause the bubble to collapse. Without exotic matter, the warp bubble cannot exist. The theoretical framework for warp bubbles comes from Einstein's equations of general relativity. These equations describe how mass and energy affect the curvature of spacetime. By solving these equations under specific conditions, the concept of a warp bubble emerges. Space-time manipulation on this scale requires enormous amounts of energy. Early estimates suggested the energy needed would be equivalent to converting the mass of the entire universe. Recent refinements have reduced these requirements, but they remain prohibitively high. Controlling a warp bubble presents significant challenges. Precise adjustments to the space-time curvature are necessary to steer and navigate the bubble. Any errors in manipulation could lead to catastrophic failures or unintended consequences. The stability of the warp bubble is another concern. Maintaining the bubble without it collapsing or dissipating requires continuous input of negative energy. This stability is essential for ensuring safe travel through space. Inside the warp bubble, the spacecraft and its occupants would experience normal passage of time. They would be shielded from the extreme velocities outside the bubble, avoiding the relativistic effects such as time dilation. Warp bubbles offer the potential for rapid interstellar travel. By bypassing the relativistic speed limit, a warp bubble could make journeys to distant stars feasible within a human lifetime. This could revolutionize our approach to space exploration. Theoretical studies suggest that the shape and size of the warp bubble can affect its energy requirements and stability. Optimizing these parameters could make the concept more practical, though still far beyond our current technological capabilities. Space-time manipulation through warp bubbles also has implications for our understanding of physics. It challenges existing theories and pushes the boundaries of what we know about the universe. This exploration can lead to new discoveries and advancements in fundamental physics. Despite its speculative nature, the concept of warp bubbles inspires innovative thinking. It encourages scientists to explore unconventional ideas and question established limitations. This mindset is crucial for breakthroughs in any scientific field. Research into space-time manipulation and warp bubbles remains largely theoretical. Experimental verification and practical implementation are distant goals. However, continued study can provide valuable insights and guide future technological developments. The pursuit of understanding and potentially harnessing space-time manipulation represents humanity's drive to explore and innovate. It reflects our desire to push the limits of what is possible and reach beyond our current grasp, embodying the spirit of discovery. The energy requirements for creating and sustaining a warp bubble are immense. Early estimates suggested that the energy needed would be equivalent to converting the mass of the entire universe. This presents a significant challenge for practical implementation. Refinements in the theoretical models have reduced the estimated energy requirements, but they still remain extraordinarily high. Even with these reductions, the energy needed is far beyond what our current technology can produce or harness. One of the key components in the concept of a warp bubble is exotic matter. Exotic matter is hypothesized to have negative energy density, which is necessary to create and stabilize the bubble. This negative energy counteracts the natural tendency of the bubble to collapse. Exotic matter is not something we have discovered or created in the lab. Its properties are purely theoretical at this point, and finding or synthesizing such matter is a major obstacle. Negative energy density is not observed in conventional matter, making the search for exotic matter particularly challenging. Theoretical physicists have proposed various mechanisms that could potentially produce exotic matter. One such mechanism is the Casimir effect, which creates negative energy between two closely spaced plates. However, the energy produced by the Casimir effect is minuscule and not sufficient for creating a warp bubble. Another proposal involves using quantum fields to generate negative energy. Quantum field theory suggests that vacuum fluctuations could produce regions of negative energy. However, harnessing these fluctuations in a controlled and practical manner is still purely speculative. The creation of a warp bubble would also require precise control over the distribution of exotic matter. This control is necessary to maintain the stability of the bubble and ensure it behaves as intended. The technical challenges of manipulating exotic matter on such a scale are daunting. Even if we could create exotic matter, generating the energy needed to sustain a warp bubble would be a significant hurdle. Current energy sources, such as nuclear and chemical reactions, are far too inefficient. New, highly efficient energy sources would need to be developed. Researchers are exploring the potential of antimatter as a high-energy source. Antimatter reactions release enormous amounts of energy, but even this might not be enough for a warp bubble. Additionally, producing and storing antimatter in large quantities presents its own set of challenges. Harnessing the power of dark energy, the mysterious force driving the accelerated expansion of the universe, is another theoretical possibility. However, our understanding of dark energy is limited, and we are far from being able to manipulate it for practical purposes. The energy requirements for a warp drive also depend on the shape and configuration of the warp bubble. Some models suggest that certain shapes could reduce the energy needed, making the concept slightly more feasible. However, these configurations are still highly theoretical. The pursuit of exotic matter and the energy needed for warp bubbles pushes the boundaries of modern physics. It challenges our understanding of the fundamental forces and particles that make up the universe. This research is at the cutting edge of theoretical and experimental physics. Theoretical breakthroughs in this area could have wide-ranging implications. Even if practical warp drives remain out of reach, the knowledge gained from studying exotic matter and high-energy physics could lead to new technologies and scientific advancements in other fields. Despite the challenges, the pursuit of warp bubbles and faster-than-light travel continues to inspire scientists and engineers. The dream of exploring distant stars and galaxies drives innovation and fuels our desire to push the limits of what is possible. The energy requirements and the search for exotic matter highlight the immense challenges of achieving faster-than-light travel. However, they also underscore the importance of continued research and exploration in our quest to understand and harness the universe's deepest secrets. Theoretical models for faster-than-light travel rely heavily on complex equations derived from Einstein's general relativity. These equations describe how mass and energy warp the fabric of space-time, which is fundamental to understanding concepts like warp bubbles and wormholes. One of the primary equations used in these models is the Einstein field equation. This equation relates the curvature of space-time to the distribution of mass and energy within it. Solutions to this equation under specific conditions can describe phenomena like black holes and, theoretically, wormholes. For the Alcubierre drive, the solution involves a specific metric that creates a warp bubble. The Alcubierre metric modifies the space-time interval, allowing a region of space to move faster than light relative to an outside observer. This requires manipulating the components of the metric tensor in Einstein's equations. The energy-momentum tensor is another critical component. It represents the density and flux of energy and momentum in space-time. For a warp bubble, the energy-momentum tensor would need to include contributions from exotic matter with negative energy density. To sustain a warp bubble, the stress-energy tensor must be finely tuned. This tensor describes the distribution and flow of energy and momentum, including the effects of pressure and stress. Ensuring stability and consistency in the warp bubble requires precise control over these quantities. Mathematical models also explore the geometry of wormholes. The Einstein-Rosen bridge, or a traversable wormhole, requires a specific solution to the Einstein field equations that connects two separate points in space-time. These solutions typically involve exotic matter to keep the throat of the wormhole open. Morris-Thorne wormholes are a specific type of traversable wormhole. The Morris-Thorne metric provides a framework for describing these wormholes, outlining the conditions necessary for their stability and traversability. This includes ensuring that the wormhole throat does not collapse. Quantum field theory is often integrated into these models to explore the effects of quantum fluctuations on spacetime. The Casimir effect, for example, shows how quantum fields can produce negative energy. This effect is studied to understand its potential role in creating or stabilizing warp bubbles and wormholes. The equations governing these phenomena are highly nonlinear and require advanced mathematical techniques to solve. Numerical simulations and computational models are often employed to explore potential solutions and behaviors under various conditions. Energy conservation and the second law of thermodynamics present additional challenges. These fundamental principles must be accounted for in any theoretical model. Ensuring that energy requirements do not violate these laws is a crucial aspect of developing feasible theories. Theories of quantum gravity, such as string theory and loop quantum gravity, aim to reconcile general relativity with quantum mechanics. These theories propose additional dimensions and fundamental particles that could influence the behavior of spacetime on very small scales. They offer potential insights into the conditions necessary for faster-than-light travel. In string theory, for instance, the geometry of extra dimensions could allow for shortcuts through spacetime, analogous to wormholes. These models use complex mathematical structures called Calabi-Yau manifolds to describe the shape and properties of these extra dimensions. Loop quantum gravity, on the other hand, attempts to quantize spacetime itself, proposing a discrete structure at the Planck scale. This theory suggests that spacetime could have a granular structure, potentially allowing for new forms of spacetime manipulation. The mathematical rigor of these models provides a foundation for exploring the physical feasibility of faster-than-light travel. While experimental verification remains a distant goal, the development of these theoretical frameworks continues to push the boundaries of our understanding. Continued advancements in mathematics and computational techniques are essential for refining these models. As our tools and methods improve, we can explore these theoretical landscapes with greater precision, bringing us closer to understanding the true potential of faster-than-light travel. Potential applications of faster-than-light travel are vast and transformative. One of the most exciting possibilities is interstellar exploration. With this technology, humanity could reach distant star systems within a reasonable time frame, opening up new frontiers for discovery and settlement. Another significant application lies in rapid transportation within our own solar system. Faster-than-light travel could drastically reduce travel times between planets, making human colonization of Mars, the moons of Jupiter, and other celestial bodies more feasible and sustainable. Scientific research would benefit enormously. Faster-than-light travel would allow for real-time data collection from distant astronomical phenomena, enhancing our understanding of the universe. This could lead to breakthroughs in physics, cosmology, and other sciences. Faster-than-light communication is another potential application. If information could travel instantaneously across vast distances, it would revolutionize the way we share knowledge and coordinate activities on a cosmic scale. This could support interstellar exploration and even intergalactic diplomacy. Medical and humanitarian missions could also see unprecedented advancements. The ability to transport supplies, personnel, and aid across vast distances in minimal time could transform responses to crises, whether on Earth or in space colonies. However, there are significant limitations to consider. The primary limitation is the current theoretical and technological barrier. The energy requirements and the need for exotic matter present challenges that we are far from overcoming with our current understanding and capabilities. Another limitation is the potential instability of faster-than-light travel mechanisms. Warp bubbles and wormholes, as currently understood, pose risks of collapse or unpredictable behavior, which could endanger travelers and missions. The ethical implications of faster-than-light travel must also be addressed. The potential for exploitation or misuse of this technology is high, and international regulations and agreements would be necessary to ensure it is used responsibly and equitably. Environmental impacts are another concern. Manipulating space-time on such a scale could have unforeseen consequences for the surrounding environment, both in space and potentially on planetary bodies. Rigorous studies would be needed to mitigate any adverse effects. Economic factors cannot be ignored. The development, deployment, and maintenance of faster-than-light travel technologies would be immensely costly. This could limit access to wealthy nations or organizations, exacerbating global inequalities. Social and psychological effects on travelers are also important to consider. The experience of such high-speed travel and the potential isolation of distant space colonies could have significant impacts on human health and social dynamics. Navigational challenges present another limitation. Accurate control and prediction of travel paths through manipulated space-time are essential to avoid catastrophic errors. Advanced technologies and algorithms would be needed to ensure safe and precise navigation. Interference with existing technologies and infrastructure must also be considered. The introduction of faster-than-light travel could disrupt current space travel methods, satellite communications, and even terrestrial technologies in unpredictable ways. Legal and territorial disputes could arise from the newfound ability to reach and claim distant territories quickly. International laws and agreements would need to evolve to address the complexities introduced by faster-than-light capabilities. Theoretical limitations also persist. Many of the current models for faster-than-light travel are based on unproven physics. As our understanding of fundamental forces and particles evolves, these models may need significant revision or could be invalidated altogether. In summary, while the potential applications of faster-than-light travel are extraordinary and could revolutionize many aspects of human life and exploration, the limitations and challenges are equally significant. Overcoming these hurdles will require unprecedented advancements in science, technology, and international cooperation. Tachyons are hypothetical particles that travel faster than the speed of light. The concept of tachyons emerges from solutions to the equations of special relativity. They were first proposed by physicist Gerald Feinberg in 1967. The term tachyon comes from the Greek word tachys, meaning swift. These particles, if they exist, would always move faster than light. Unlike ordinary particles, tachyons would increase in speed as they lose energy. One of the key properties of tachyons is their imaginary mass. In the equations of special relativity, a particle with imaginary mass results in a speed greater than that of light. This distinguishes tachyons from other known particles with real positive mass. Tachyons would exhibit unusual behavior compared to familiar particles. For instance, as they lose energy, their speed increases. This is the opposite of what happens with normal particles, where losing energy results in slower speeds. If tachyons exist, they could have profound implications for our understanding of causality. Traveling faster than light, tachyons could, in theory, move backward in time. This would introduce the possibility of effects preceding their causes, leading to potential paradoxes. The theoretical existence of tachyons does not necessarily violate the principles of special relativity. Instead, They exist within a different framework, where the standard rules of causality and energy-mass relationships are altered. This makes them a fascinating topic of study in theoretical physics. Tachyons have not been detected experimentally. Their existence remains purely hypothetical. Physicists have devised numerous experiments to search for evidence of tachyons, but none have confirmed their presence so far. If tachyons do exist, they might interact weakly with normal matter. This weak interaction could make them extremely difficult to detect with current technology. Scientists continue to explore new methods and technologies that might reveal these elusive particles. Tachyons have been a popular subject in science fiction. They often appear as a plot device to enable faster-than-light travel or communication. These fictional representations, while imaginative, often simplify the complex theoretical nature of tachyons. In quantum field theory, tachyons can appear as instabilities in a system. These are not physical particles, but rather indicators that the system might settle into a more stable state. This theoretical concept helps physicists understand potential phase transitions in quantum fields. The mathematical framework for tachyons involves complex numbers. Their imaginary mass introduces new dimensions to the equations of motion. These mathematical properties are consistent within the theory, but challenge our conventional understanding of physics. Some theories suggest that if tachyons exist, they could emit Cherenkov radiation in a vacuum. This is analogous to the radiation emitted by particles moving faster than the speed of light in a medium, like water. Detecting such radiation could be a way to identify tachyons. Tachyons also have implications for string theory. In some versions of string theory, tachyons represent unstable states that the strings can occupy. These states can lead to symmetry breaking, an important concept in understanding the fundamental forces of nature. Despite their speculative nature, the study of tachyons pushes the boundaries of theoretical physics. They challenge physicists to think beyond the standard models and consider new possibilities for the behavior of particles and the nature of the universe. The quest to understand tachyons, whether they exist or not, continues to drive innovation in theoretical and experimental physics. It opens new avenues for research and helps refine our models of the universe, even as it sparks the imagination of scientists and science fiction enthusiasts alike. The concept of particles traveling faster than light predates the formal introduction of tachyons. Early 20th century physicists, grappling with the implications of Einstein's special relativity, speculated about hypothetical particles that could break the light-speed barrier. In 1962, Belaniuk, Deshpande, and Sudarshan explored the idea of faster-than-light particles. They published a paper discussing the theoretical properties of such particles, laying the groundwork for future discussions. Their work was pivotal in bringing the concept into mainstream theoretical physics. Gerald Feinberg coined the term tachyon in 1967. His paper, Possibility of Faster-than-Light Particles, proposed that particles with imaginary mass could travel faster than light. Feinberg's work provided a mathematical framework for understanding these hypothetical particles. Feinberg's proposal was based on the equations of special relativity. He showed that if particles had an imaginary mass, they could theoretically exceed the speed of light without violating the principles of relativity. This idea sparked significant interest and debate among physicists. During the 1970s, interest in tachyons grew. Physicists explored their potential implications for causality and the structure of space-time. Some researchers investigated how tachyons might interact with normal matter and what experimental signatures they might produce. Tachyons also influenced the development of quantum field theory. Theoretical physicists considered how tachyons could appear as instabilities in quantum fields. This led to insights into the behavior of fields and the conditions under which phase transitions might occur. The potential for tachyons to violate causality intrigued many scientists. If tachyons could travel backward in time, they could create paradoxes where effects precede their causes. This aspect of tachyons made them a fascinating, albeit controversial, topic of study. Despite the theoretical interest, experimental searches for tachyons have been inconclusive. Various experiments have attempted to detect faster-than-light particles, but none have provided definitive evidence. The elusive nature of tachyons remains a significant challenge. Tachyons have also found a place in popular culture. Science fiction writers and filmmakers have used the concept to explore themes of faster-than-light travel, time travel, and advanced communication technologies. These imaginative uses have helped popularize the idea. In the context of string theory, tachyons represent unstable states that can lead to the breaking of symmetries. This perspective has provided new ways to think about the role of tachyons in theoretical physics, linking them to fundamental aspects of particle physics and cosmology. The historical context of tachyons is marked by periods of intense theoretical exploration. While the initial excitement has waned somewhat, the concept continues to inspire new ideas and investigations. Tachyons remain a symbol of the quest to push the boundaries of known physics. Throughout the decades, the debate over tachyons has highlighted the interplay between theoretical predictions and experimental verification. The challenge of detecting tachyons underscores the limits of current technology and the need for innovative experimental techniques. The exploration of tachyons has also contributed to broader discussions about the nature of space-time. These discussions have helped refine our understanding of relativity and quantum mechanics, even if tachyons themselves remain hypothetical. The legacy of tachyon research is evident in the ongoing quest to understand faster-than-light phenomena. Whether tachyons exist or not, the theoretical frameworks developed to study them continue to influence modern physics. The story of tachyons illustrates the dynamic nature of scientific inquiry. It shows how theoretical predictions can drive experimental efforts and how even speculative ideas can lead to significant advancements in our understanding of the universe. Tachyons could theoretically exceed light speed due to their unique properties in the equations of special relativity. Unlike ordinary particles with real mass, tachyons possess an imaginary mass, which allows them to travel faster than light without violating relativistic principles. In the framework of special relativity, a particle with imaginary mass behaves differently from one with real mass. As a tachyon loses energy, its speed increases. This is in stark contrast to normal particles, which slow down as they lose energy. The energy-momentum relation for tachyons is altered by their imaginary mass. This relationship implies that, for tachyons, velocity exceeds the speed of light even at low energy levels. Consequently, their speed cannot drop below the speed of light, making them inherently superluminal. Tachyons theoretically move faster than light from the moment they are created. They would never travel at or below the speed of light, avoiding the infinite energy requirement that regular particles face as they approach light speed. This fundamental difference allows tachyons to bypass the light speed limit imposed on ordinary matter. If tachyons exist, they could communicate information instantaneously over vast distances. Their superluminal speeds would enable signals to be sent faster than light, potentially revolutionizing our understanding of communication and causality. This theoretical property intrigues scientists and science fiction writers alike. One fascinating aspect of tachyons is their potential to move backward in time. Due to their superluminal speeds, they could theoretically arrive at a destination before they left. This time-reversing characteristic introduces intriguing possibilities and paradoxes in the realm of causality. In quantum field theory, tachyons are represented as fields with negative mass squared. These fields are often associated with instabilities, indicating that a system might transition to a more stable state. This interpretation helps physicists understand how tachyons might fit within broader physical theories. Despite their theoretical properties, detecting tachyons poses significant challenges. Their weak interaction with normal matter and their unique behavior make them difficult to observe with current experimental techniques. Advanced detectors and novel approaches would be needed to confirm their existence. Some theories suggest that tachyons might manifest in high-energy cosmic events. These events could produce conditions where tachyons are generated, providing a potential avenue for their detection. Researchers continue to explore cosmic phenomena for indirect evidence of tachyons. The potential for tachyons to violate causality has led to various theoretical debates. If tachyons can travel back in time, they could create paradoxes where an effect precedes its cause. Resolving these paradoxes would require new insights into the nature of time and causality. Physicists have proposed that tachyons might be confined to specific regions or conditions in the universe. These constraints could explain why we have not yet observed them. Studying these conditions might reveal more about where and how tachyons could exist. The mathematical models describing tachyons are consistent within the framework of special relativity. These models provide a basis for understanding their properties and behaviors. However, translating these mathematical concepts into physical reality remains a significant challenge. Tachyons, if they exist, could provide a new window into the fundamental forces of nature. Their unique properties might reveal unknown aspects of space-time and energy. This potential drives continued theoretical exploration and experimental efforts. The study of tachyons also impacts our understanding of other theoretical constructs, like wormholes and warp drives. These concepts often rely on similar principles of superluminal travel and exotic matter. Insights gained from tachyon research could inform these broader theories. Theoretical exploration of tachyons continues to push the boundaries of modern physics. While their existence remains unconfirmed, the pursuit of understanding tachyons encourages innovative thinking and drives the development of new scientific methods and technologies. Detecting tachyons presents numerous challenges due to their hypothetical nature and unique properties. Since they travel faster than light, traditional detection methods, which rely on observing slower-than-light particles, are inadequate. One significant challenge is the weak interaction between tachyons and normal matter. Tachyons, if they exist, might not interact with conventional particles in a way that produces detectable signals. This makes it difficult to observe them using existing technology. Theoretical models suggest tachyons could emit Cherenkov radiation in a vacuum, analogous to how particles emit light when traveling faster than light in a medium like water. However, designing experiments to detect such radiation in space or a controlled environment is complex and untested. Another challenge lies in the creation of tachyons under controlled conditions. Current particle accelerators are designed to accelerate particles with real mass. Developing new technology to produce and study particles with imaginary mass is a daunting task requiring significant advancements in experimental physics. Even if tachyons could be created, capturing or measuring them is problematic. Their superluminal speed means they would traverse detection equipment almost instantaneously, potentially without leaving a trace. New types of detectors capable of registering such rapid events are necessary. The potential backward time travel property of tachyons introduces further complications. If tachyons can travel back in time, their detection might require equipment that can identify particles appearing before the detection event itself, challenging our conventional understanding of causality and time. Exotic conditions might be required to detect tachyons. Some theories propose they could be more readily observable in extreme environments, such as near black holes or during high-energy cosmic events. Replicating these conditions on Earth or designing space-based experiments is highly challenging. Mathematical models and simulations are crucial in guiding the search for tachyons. These models help predict where and how tachyons might manifest. However, the accuracy of these predictions depends on the validity of the underlying theoretical frameworks, which remain speculative. Using tachyons for practical applications, such as faster-than-light communication, is even more complex. Harnessing tachyons would require not only detecting them, but also controlling their production and behavior. Tasks far beyond current technological capabilities. And theoretical debates continue about the implications of utilizing tachyons. If tachyons could be harnessed, they might allow instantaneous communication across vast distances. However, this raises questions about information security, latency, and the fundamental limits of data transmission. Ethical and philosophical considerations also emerge when discussing tachyon utilization. The potential to manipulate time and causality poses significant moral and philosophical dilemmas, particularly concerning free will and the nature of reality. Research into tachyons could lead to unintended consequences. The manipulation of exotic particles and high-energy phenomena might pose risks we do not yet understand. Comprehensive safety measures and ethical guidelines would be essential. Collaboration across multiple disciplines is necessary to address these challenges. Physicists, engineers, and philosophers must work together to explore the theoretical and practical aspects of tachyons, ensuring a holistic approach to their study and potential application. The pursuit of tachyons drives innovation in theoretical and experimental physics. Each challenge encourages the development of new technologies and methodologies, contributing to the broader field of scientific research. even if tachyons themselves remain elusive. The challenges in detecting and utilizing tachyons highlight the limits of our current scientific understanding. However, they also represent an opportunity to push the boundaries of what we know and to explore the fundamental principles that govern our universe. Current research into tachyons is primarily theoretical, exploring their implications and potential existence within the framework of modern physics. Physicists are using advanced mathematical models to understand how tachyons might fit into the known laws of the universe. String theory is one area where tachyons play a significant role. In certain versions of string theory, tachyons appear as indicators of instability in a system. These instabilities can lead to phase transitions, helping researchers understand fundamental forces and particles. Quantum field theory also examines the role of tachyons. In this context, tachyons can be seen as fields with imaginary mass, contributing to our understanding of vacuum states and potential new physics. These studies help refine the models that describe the universe at its most basic level. Some researchers are looking at how tachyons might interact with black holes. The extreme conditions around black holes provide a unique environment where the effects of faster-than-light particles could be more apparent. This research could offer indirect evidence of tachyons. High-energy particle physics experiments like those conducted at CERN continue to search for anomalies that could hint at the existence of tachyons. While no direct evidence has been found, these experiments help to rule out certain theoretical models and refine our understanding. Astrophysicists are exploring cosmic rays and other high-energy phenomena in space for signs of tachyons. Cosmic rays, which are highly energetic particles from outer space, might interact in ways that could reveal the presence of faster-than-light particles. Researchers are also investigating the possibility that tachyons could be produced in particle collisions. By studying the results of these high-energy collisions, scientists hope to identify patterns or anomalies that could suggest the existence of tachyons. Theoretical models are being developed to predict the behavior of tachyons under various conditions. These models help guide experimental searches by suggesting where and how tachyons might be detected. They also provide a framework for understanding the implications of their existence. Some physicists are exploring the concept of tachyon condensation. This process, where tachyons could condense into a lower energy state, might help explain certain phenomena in string theory and quantum field theory. It provides a potential mechanism for resolving instabilities in these theories. Quantum entanglement is another area where tachyons are being studied. The idea is that tachyons might play a role in the instant connection between entangled particles, offering a new perspective on this mysterious quantum phenomenon. Tachyons are also being considered in the context of dark energy. Some theories propose that the properties of tachyons could help explain the accelerated expansion of the universe. This research could bridge the gap between particle physics and cosmology. Despite the lack of experimental evidence, the study of tachyons continues to drive theoretical advancements. Each new model and theory contributes to a deeper understanding of the fundamental nature of the universe, even if tachyons themselves remain elusive. Collaboration between theoretical physicists and experimentalists is crucial. By working together, they can design experiments that test the predictions of tachyon models, helping to refine our understanding of high-energy physics and potential faster-than-light particles. The search for tachyons also encourages the development of new technologies. Advanced detectors, high-energy particle accelerators, and sophisticated data analysis methods are all being refined in the quest to identify these hypothetical particles. Ultimately, the current research and theories surrounding tachyons represent the cutting edge of physics. They challenge our understanding, push the boundaries of what is known, and inspire new questions about the fundamental nature of reality. Quantum mechanics is the branch of physics that deals with the behavior of particles at the smallest scales. It describes the bizarre and counterintuitive ways that particles like electrons and photons interact and move. At the heart of quantum mechanics is the wave-particle duality. This principle states that particles can exhibit both wave-like and particle-like properties. For example, light can behave as both a wave and a stream of particles called photons. One of the key concepts in quantum mechanics is the uncertainty principle. Proposed by Werner Heisenberg, It states that certain pairs of physical properties, like position and momentum, cannot be simultaneously measured with perfect accuracy. This inherent uncertainty is a fundamental feature of the quantum world. Quantum mechanics also introduces the idea of quantization. Energy levels in atoms and other systems are discrete, not continuous. This means particles can only exist in specific energy states, and transitions between these states involve quantized amounts of energy. Another fundamental concept is superposition. Quantum particles can exist in multiple states at once until measured. This principle is famously illustrated by Schrödinger's cat, a thought experiment where a cat in a box is simultaneously alive and dead until observed. Quantum entanglement is a phenomenon where particles become interconnected, such that the state of one instantly influences the state of another, regardless of distance. This spooky action at a distance, as Einstein called it, challenges our classical understanding of locality. Quantum tunneling is a direct result of the wave-like nature of particles. It allows particles to pass through energy barriers that would be insurmountable according to classical physics. This occurs because the particle's wave function extends through the barrier, giving it a non-zero probability of being on the other side. Tunneling is critical to many natural and technological processes. In the Sun, it enables nuclear fusion by allowing protons to overcome repulsive forces and fuse together. This process powers the Sun and other stars, making life on Earth possible. In electronics, quantum tunneling is essential for the operation of devices like tunnel diodes and quantum computers. These devices exploit tunneling to achieve high-speed operations and new computational capabilities beyond classical limits. The mathematics of quantum tunneling involves solving the Schrödinger equation for a particle encountering a potential barrier. The solutions reveal that there is always a finite probability that the particle will tunnel through the barrier, depending on its energy and the barrier's width and height. Quantum tunneling also plays a role in radioactive decay. Certain nuclei are unstable and can decay into more stable forms by emitting particles. Tunneling allows these particles to escape the nucleus, despite the potential barrier formed by nuclear forces. Understanding tunneling provides insight into the fundamental workings of the quantum world. It challenges our classical intuitions and reveals the probabilistic nature of quantum mechanics, where outcomes are not deterministic, but instead described by probabilities. The implications of quantum mechanics and tunneling extend to many fields, from chemistry to cosmology. They help explain the behavior of atoms and molecules, the formation of stars, and the underlying principles governing the universe. As researchers continue to explore quantum mechanics, they uncover new phenomena and develop advanced technologies. The ongoing study of tunneling and other quantum effects promises to revolutionize various industries and deepen our understanding of the natural world. The basics of quantum mechanics and tunneling highlight the strange and fascinating nature of the quantum realm. They reveal a universe that operates very differently from the macroscopic world we experience daily, challenging and expanding our notions of reality. Particles tunnel through barriers due to the principles of quantum mechanics. Unlike classical particles, which are strictly confined by energy barriers, quantum particles have a wave-like nature that allows them to penetrate and pass through these barriers. The wave function of a particle describes its quantum state and contains all the information about its position and momentum. When a quantum particle encounters a barrier, its wave function does not abruptly stop, but instead gradually decreases in amplitude as it penetrates the barrier. Even though the wave function diminishes inside the barrier, it never entirely goes to zero. This means there is a finite probability that the particle can be found on the other side of the barrier. The likelihood of tunneling depends on the height and width of the barrier and the energy of the particle. To understand this better, consider a potential barrier that a particle must overcome. Classically, if the particle's energy is less than the barrier's height, it cannot cross. However, quantum mechanically, there is still a chance for the particle to tunnel through due to the non-zero wave function within the barrier. Mathematically, this phenomenon is described by solving the Schrödinger equation for the particle's wave function in the presence of the potential barrier. The solutions show that the wave function decays exponentially within the barrier, but re-emerges on the other side, indicating tunneling. The probability of tunneling is higher if the barrier is thinner, or if the particle's energy is closer to the barrier's height. Conversely, thicker barriers or much higher barriers relative to the particle's energy reduce the tunneling probability significantly. Quantum tunneling is not just a theoretical concept, but has observable consequences. In semiconductors, for example, electrons tunnel through energy barriers between different materials, allowing current to flow in tunnel diodes and other electronic components. In nuclear physics, tunneling explains the process of alpha decay. In this process, an alpha particle within a nucleus tunnels through the nuclear potential barrier to escape, leading to radioactive decay. Without tunneling, many radioactive elements would be much more stable. The concept of tunneling is also crucial in the field of quantum computing. Quantum bits, or qubits, leverage tunneling to transition between different states quickly, enabling the high-speed computations that classical bits cannot achieve. Tunneling plays a role in biological processes as well. Enzymes, for example, often use quantum tunneling to facilitate biochemical reactions at speeds much faster than would be possible through classical mechanisms alone. Another fascinating application is in the scanning tunneling microscope, STM, which uses tunneling to image surfaces at the atomic level. An STM measures the tunneling current between a sharp metal tip and the surface being examined, providing incredibly detailed images. Quantum tunneling highlights the non-intuitive nature of the quantum world. Particles can bypass classical constraints, showing that our classical understanding of impenetrable barriers does not apply at the quantum scale. This phenomenon demonstrates the probabilistic nature of quantum mechanics. Unlike classical mechanics, which predicts definite outcomes, quantum mechanics provides probabilities for various outcomes, with tunneling being a prime example of these probabilistic events. The study of tunneling continues to advance our understanding of quantum mechanics and leads to technological innovations. As we develop more sophisticated tools and techniques, we are likely to discover even more applications and implications of quantum tunneling. Understanding how particles tunnel through barriers challenges our classical intuitions and opens up new possibilities in science and technology. It underscores the power and mystery of quantum mechanics, revealing a universe full of surprising and counterintuitive behaviors. Quantum tunneling's implications for faster-than-light travel are profound and speculative. This phenomenon suggests that particles can bypass the classical constraints of energy barriers, hinting at possibilities beyond our current understanding of physics. If particles can tunnel through barriers instantaneously, it raises questions about the limits of speed in the quantum realm. This challenges the traditional view that nothing can travel faster than light, as tunneling appears to circumvent this limit. One potential implication is the development of new propulsion systems. If we can harness tunneling effects on a macroscopic scale, it might enable spacecraft to move through space in ways that are currently unimaginable, potentially achieving superluminal speeds. Tunneling also suggests new methods for communication. If information could be transmitted using quantum tunneling, it might allow for instantaneous communication across vast distances, overcoming the limitations imposed by the speed of light. The study of tunneling effects in different materials and environments could lead to breakthroughs in creating and stabilizing wormholes or warp bubbles. These theoretical constructs rely on exotic matter and energy conditions, which might be better understood through quantum tunneling research. Quantum entanglement, closely related to tunneling, further expands the possibilities. Entangled particles can affect each other instantaneously, regardless of distance. This phenomenon hints at mechanisms that might support faster-than-light interactions. Researchers are exploring whether tunneling could be scaled up from the quantum level to the macroscopic level. This involves understanding and controlling quantum coherence over larger distances and timescales, a significant challenge but a necessary step toward practical applications. Theoretical models incorporating tunneling could refine our understanding of space-time. These models might reveal new aspects of the universe's structure, potentially offering pathways for faster-than-light travel that do not violate relativity. Quantum tunneling could also impact our understanding of black holes and the event horizon. If particles can tunnel out of black holes, it might resolve some paradoxes associated with information loss, shedding light on the nature of these enigmatic objects. Experimental advances in quantum tunneling might lead to discovering new particles or forces. These discoveries could provide the exotic matter or negative energy needed for faster-than-light travel concepts, such as the Alcubierre drive or traversable wormholes. The implications extend to our understanding of causality. Faster-than-light travel could result in time paradoxes, where cause and effect are reversed. Quantum mechanics' probabilistic nature might offer solutions to these paradoxes, helping to reconcile them with physical laws. Quantum tunneling also suggests new energy sources. If we can control tunneling efficiently, it might provide a way to tap into previously inaccessible energy levels, potentially revolutionizing power generation and propulsion technologies. The potential to manipulate spacetime using tunneling effects could lead to novel transportation methods. These methods might not only allow for faster-than-light travel, but also enable new forms of teleportation or instantaneous travel within localized regions. The continued study of quantum tunneling and its implications for faster-than-light travel requires interdisciplinary collaboration. Physicists, engineers, and technologists must work together to explore these possibilities, combining theoretical insights with practical experimentation. As our understanding of quantum mechanics deepens, the boundaries of what is possible will continue to expand. The implications of quantum tunneling for faster-than-light travel represent just one frontier in this ongoing journey of discovery, pushing us to rethink the fundamental limits of our universe. Experimental evidence for faster-than-light travel remains elusive. Most current experiments focus on testing the boundaries of special relativity and the speed of light as a cosmic speed limit. So far, no experiment has definitively demonstrated superluminal travel. However, quantum tunneling experiments show that particles can exhibit behaviors that challenge classical notions of speed and barriers. These experiments involve electrons and other particles tunneling through potential barriers, appearing on the other side almost instantaneously. One famous experiment demonstrating quantum tunneling is the scanning tunneling microscope. It uses the tunneling effect to create images of surfaces at the atomic level. While this does not directly indicate faster-than-light travel, it underscores the strange behaviors particles can exhibit. Theoretical models continue to evolve, exploring how the principles observed in quantum tunneling might be applied on larger scales. These models often involve complex mathematics and concepts from quantum field theory and general relativity. One such model is the concept of quantum teleportation. While not faster than light travel in the traditional sense, quantum teleportation allows for the instant transfer of quantum states between entangled particles. This phenomenon hints at potential superluminal communication methods. Researchers are also examining the properties of hypothetical particles like tachyons, which would inherently travel faster than light. While tachyons have not been detected, their theoretical properties challenge and expand our understanding of particle physics. In high-energy physics, experiments like those conducted at CERN with the Large Hadron Collider search for anomalies that might suggest new particles or forces. These could potentially lead to discoveries relevant to faster-than-light travel theories. Theoretical work on wormholes, or Einstein-Rosen bridges, explores how these structures could connect distant points in space-time, effectively allowing faster-than-light travel. These models require exotic matter to keep the wormhole stable, a concept still purely theoretical. Another promising area of research is the study of dark energy and its effects on the expansion of the universe. Some theories suggest that understanding dark energy could reveal new methods for manipulating space-time and achieving faster-than-light travel. Experimental physicists are also investigating the Casimir effect, where quantum fluctuations between two closely spaced plates create negative energy. This phenomenon might provide insights into generating the exotic matter needed for theoretical faster-than-light travel constructs. Advances in quantum computing and quantum information science are providing new tools for exploring these theories. Quantum simulations and high-precision experiments are pushing the boundaries of what we can test and observe at the quantum level. Mathematical models like the Alcubierre drive propose a way to achieve faster-than-light travel by contracting and expanding space-time around a spacecraft. While purely theoretical, these models are grounded in the equations of general relativity and offer a framework for further exploration. Some researchers propose that observing high-energy cosmic phenomena, such as gamma-ray bursts or neutrino emissions, might provide indirect evidence of faster-than-light particles or effects. These observations require highly sensitive instruments and advanced data analysis techniques. Collaboration between experimentalists and theorists is crucial in this field. Experimental results inform theoretical models, while new theories guide the design of experiments. This iterative process is essential for advancing our understanding of faster-than-light travel possibilities. Despite the challenges, the pursuit of experimental evidence and the development of theoretical models for faster-than-light travel represent the cutting edge of modern physics. Each discovery, whether confirming or refuting these ideas, brings us closer to understanding the true limits and possibilities of our universe. The limitations and practical challenges of faster-than-light travel are significant. One of the primary issues is the enormous energy requirement. According to current models, achieving superluminal speeds would require vast amounts of energy, far beyond what we can currently generate or store. Exotic matter, which is essential for many faster-than-light travel theories, presents another major hurdle. This hypothetical form of matter has properties that are not observed in any known particles. Creating or discovering exotic matter is a significant challenge that remains unsolved. Even if exotic matter could be produced, maintaining stability during faster-than-light travel is a daunting task. Theoretical constructs like warp bubbles and wormholes require precise control to prevent collapse or other catastrophic failures during travel. Navigational control at faster-than-light speeds poses its own set of challenges. Traditional methods of navigation and course correction may not apply when traveling through manipulated space-time. Developing new technologies for precise control and guidance is essential. The effects of faster-than-light travel on human physiology are unknown. The extreme conditions involved, including potential exposure to exotic matter or intense gravitational fields, could pose significant risks to travelers. Understanding and mitigating these effects is critical for manned missions. Communication during faster-than-light travel is another unresolved issue. Traditional signals, which travel at or below the speed of light, would be ineffective for real-time communication with a superluminal spacecraft. New methods of communication must be developed. The potential for time paradoxes and causality violations is a profound theoretical challenge. Faster-than-light travel could allow for backward time travel, leading to scenarios where cause and effect are reversed. Resolving these paradoxes is crucial for consistent physical laws. The financial cost of developing faster-than-light travel technology is prohibitive. Research, development, and construction of the necessary infrastructure would require unprecedented investment. This raises questions about funding and the economic feasibility of such projects. Regulatory and legal frameworks for faster-than-light travel do not currently exist. International agreements and regulations would be necessary to manage the use of this technology, including issues of sovereignty, space traffic control, and potential militarization. The environmental impact of manipulating spacetime on such a scale is unknown. Potential side effects could include unintended changes to local spacetime, which might have unforeseen consequences for both space and planetary environments. Interference with existing space missions and satellites is another concern. The introduction of faster-than-light travel could disrupt current space operations, requiring new protocols and coordination efforts to ensure the safety and functionality of existing systems. The ethical implications of faster-than-light travel are significant. Issues such as equitable access to this technology, the potential for exploitation, and the consequences of encountering extraterrestrial life must be carefully considered and addressed. Public perception and acceptance of faster-than-light travel will also play a role. Overcoming skepticism and addressing concerns about safety and ethical implications will be essential for gaining widespread support and participation in these endeavors. Technological limitations in our current understanding of quantum mechanics and general relativity also pose challenges. Many of the theories and models for faster-than-light travel rely on concepts that are not yet fully understood or proven. Advancing our knowledge in these areas is essential. Despite these limitations and challenges, the pursuit of faster-than-light travel continues to drive innovation and exploration in physics. Overcoming these obstacles will require a collaborative, interdisciplinary effort and a willingness to push the boundaries of what is currently possible. Faster-than-light travel, often abbreviated as FTL, refers to the hypothetical ability to move or communicate at speeds exceeding the speed of light in a vacuum, which is approximately 299,792 kilometers per second. The concept of FTL travel challenges our current understanding of physics particularly the theories of special and general relativity proposed by Albert Einstein. According to these theories, the speed of light is the ultimate speed limit in the universe. One theoretical framework that explores FTL travel is the idea of warp drives, such as the Alcubierre drive. This concept involves creating a warp bubble that contracts spacetime in front of a spacecraft and expands it behind, effectively allowing the spacecraft to move faster than light relative to an outside observer. Another prominent theoretical model involves wormholes, also known as Einstein-Rosen bridges. Wormholes are theoretical passages through spacetime that could create shortcuts between distant points in the universe, potentially enabling FTL travel. Theoretical physicists have also considered the possibility of tachyons, hypothetical particles that travel faster than light. These particles would have imaginary mass and could, in theory, provide insights into FTL phenomena. Exotic matter with negative energy density is often cited as a necessary component for stabilizing wormholes or creating warp bubbles. This type of matter has properties that differ significantly from normal matter, making it a crucial yet elusive element in FTL theories. Quantum mechanics introduces additional complexities to the discussion of FTL travel. Concepts such as quantum entanglement suggest that particles can affect each other instantaneously over vast distances, hinting at potential mechanisms for superluminal communication. Theoretical models also explore the implications of dark energy and the accelerated expansion of the universe. Understanding these cosmic forces could reveal new methods for manipulating space-time and achieving FTL travel. Mathematical equations derived from general relativity, such as the Einstein field equations, provide a foundation for exploring these theoretical constructs. These equations describe how mass and energy warp the fabric of space-time, leading to potential FTL solutions. Despite the intriguing possibilities, the existence of FTL travel remains purely theoretical. No experimental evidence has yet confirmed the feasibility of these concepts, and many challenges must be overcome to translate theory into practice. One major challenge is the enormous energy requirement for creating and sustaining FTL travel mechanisms. Current technological capabilities are far from being able to generate the vast amounts of energy needed for these theoretical constructs. Another challenge is the stability of FTL travel methods. Theoretical models often involve unstable configurations that could collapse or behave unpredictably, posing significant risks to any attempt at practical implementation. The effects of FTL travel on spacetime and causality are also a major area of concern. The possibility of time paradoxes, where cause and effect are reversed, raises profound questions about the consistency of physical laws. Interdisciplinary collaboration is essential for advancing our understanding of FTL travel. Physicists, engineers, and other scientists must work together to explore the theoretical and practical aspects of these concepts, pushing the boundaries of our knowledge. The pursuit of FTL travel continues to inspire both scientific inquiry and the imagination. While it remains a speculative field, the ongoing research and exploration of FTL theories hold the potential to revolutionize our understanding of the universe and our place within it. Cosmic strings are hypothetical one-dimensional defects in the fabric of spacetime, predicted by certain theories in particle physics and cosmology. These strings are incredibly thin, but possess immense mass and tension. One of the fascinating properties of cosmic strings is their ability to warp spacetime around them. This warping effect could theoretically create conditions favorable for faster-than-light travel. If two cosmic strings were to pass close to each other, they could create a region of highly curved spacetime. This phenomenon is known as a string interaction and could form a tunnel-like structure through spacetime, potentially functioning like a wormhole. Traveling through this tunnel could allow a spacecraft to take a shortcut between two distant points in space. The spacecraft would effectively bypass the normal space in between, drastically reducing travel time. The energy and tension of cosmic strings might also generate gravitational waves, ripples in spacetime that propagate at the speed of light. These waves could further influence the structure of spacetime around the strings. In theory, a spacecraft could hitch a ride on these gravitational waves, using them to accelerate and achieve higher velocities. This concept leverages the natural properties of cosmic strings to facilitate faster travel. Cosmic strings are predicted to be remnants of the early universe, formed during phase transitions shortly after the Big Bang. They are incredibly dense, with a single string potentially stretching across the entire observable universe while being thinner than an atomic nucleus. Detecting cosmic strings is a significant challenge due to their thinness and the vast distances they span. However, their immense gravitational effects could potentially be observed through their influence on nearby objects and light. Gravitational lensing is one way to detect cosmic strings. As light from distant stars or galaxies passes near a cosmic string, it would be bent in a characteristic way, creating unique visual distortions that astronomers could identify. If cosmic strings can be found and harnessed, they might offer a new method of space travel that avoids the need for exotic matter or immense energy requirements associated with other faster-than-light travel concepts. The interaction of cosmic strings with black holes could also provide insights. The intense gravitational fields of black holes interacting with cosmic strings might create new phenomena that could be leveraged for faster travel. Researchers are also exploring the mathematical models of cosmic strings to understand their potential effects on spacetime. These models help predict how cosmic strings might behave and interact with other cosmic structures. While the existence of cosmic strings remains theoretical, ongoing advancements in observational astronomy and cosmology continue to push the boundaries of our understanding. Discovering cosmic strings would be a groundbreaking achievement with profound implications. Theoretical studies suggest that cosmic strings could connect different regions of the universe, much like wormholes. These connections might enable instant travel between distant parts of the cosmos, revolutionizing our approach to space exploration. Harnessing the properties of cosmic strings for faster-than-light travel is an exciting possibility that drives both scientific research and the imagination. If proven feasible, it would open new frontiers and transform our capability to explore the universe. One potential energy source for faster-than-light travel is antimatter. Antimatter reactions release immense amounts of energy when they come into contact with matter, making them a highly efficient power source. Another possible energy source is nuclear fusion, the same process that powers the sun. Fusion reactions could provide a continuous and powerful energy output necessary for advanced propulsion systems. Dark energy, which is responsible for the accelerated expansion of the universe, is another intriguing candidate. Harnessing dark energy could offer a way to manipulate space-time and achieve faster-than-light travel. Zero-point energy, the lowest possible energy state of a quantum mechanical system, might also be exploited. If we could tap into this pervasive background energy, it could provide a virtually limitless power source. Exotic matter with negative energy density is often theorized as a necessary component for stabilizing warp bubbles or wormholes. Finding or creating such matter remains a significant challenge, but is crucial for many faster-than-light travel concepts. Gravitational waves, ripples in space-time caused by massive objects, might also be used. Advanced technology could potentially capture and utilize these waves for propulsion or space-time manipulation. High-energy particle accelerators are another potential mechanism. By accelerating particles to near-light speeds, we could explore new states of matter and energy that might be harnessed for faster-than-light travel. Harnessing the energy of black holes is a speculative but fascinating idea. The immense gravitational energy around black holes could be converted into usable power, providing a potent source of energy for advanced spacecraft. Solar sails, which use radiation pressure from stars, could be combined with other advanced propulsion systems. While not faster than light by themselves, they could be part of a hybrid system that achieves greater speeds. Quantum entanglement could revolutionize communication methods, allowing for instant data transfer across vast distances. While not an energy source, this mechanism is crucial for maintaining control and coordination of faster-than-light missions. Harnessing the energy from cosmic strings, if they exist, is another possibility. The immense tension and mass of cosmic strings could provide a unique and powerful energy source for space travel. Fusion of exotic particles, such as hypothetical quark-gluon plasmas, might also provide new avenues for energy production. These high-energy states could offer unprecedented power densities for propulsion systems. The Casimir effect, a quantum phenomenon where vacuum fluctuations produce measurable forces, could be another potential energy source. This effect might be scaled up to provide significant power for advanced space travel. Utilizing the energy from supernovae or other cosmic events is a more extreme idea. Capturing the energy from such massive explosions could power spacecraft for extended missions across the galaxy. Finally, advancements in superconductors and materials science could lead to more efficient energy storage and transfer mechanisms. These technologies are essential for making any potential energy source viable for faster-than-light travel. Faster-than-light travel would revolutionize space exploration. It would enable humanity to reach distant star systems in a fraction of the time it takes with current technology, opening up new possibilities for colonization and resource acquisition. The ability to travel faster than light would also transform our understanding of the universe. We could explore regions of space that are currently beyond our reach, gathering data and making observations that could fundamentally change our knowledge of cosmology. Interstellar travel would become a reality. This capability could lead to the discovery of new planets, some of which might be habitable or rich in resources, providing new opportunities for scientific research and economic expansion. Faster-than-light travel would also allow us to study celestial phenomena up close. We could send missions to investigate black holes, neutron stars, and other exotic objects, gaining insights that are currently impossible with remote observations. The concept of time would be fundamentally altered. Faster-than-light travel could involve time dilation and even backward time travel, challenging our conventional notions of cause and effect, and requiring new theories to understand these phenomena. Communication across vast distances would become instantaneous. This would be crucial for coordinating interstellar missions and maintaining contact with distant colonies, ensuring that information can be shared in real time. The search for extraterrestrial life would be greatly enhanced. We could reach exoplanets in habitable zones around other stars, increasing the chances of finding and studying alien life forms and potentially making first contact. Faster-than-light travel would also have significant implications for our understanding of dark matter and dark energy. By exploring previously inaccessible regions of space, we could gather data that might help solve these fundamental mysteries of cosmology. The economics of space travel would change dramatically. Faster-than-light travel would reduce the time and cost associated with long-duration missions, making space exploration more feasible and attractive for both public and private ventures. New industries could emerge, centered around faster-than-light travel technology. This could include spacecraft manufacturing, energy production, and space tourism, creating jobs and stimulating economic growth. The ethical implications of faster-than-light travel must also be considered. Issues such as the impact on indigenous life forms, the potential for exploitation, and the equitable distribution of resources would need to be addressed. Faster-than-light travel would also necessitate new legal frameworks. International agreements and regulations would be required to manage the use of this technology, including territorial claims, space traffic control, and the prevention of conflicts. The environmental impact of faster-than-light travel on space and planetary ecosystems would need to be studied. We would have to ensure that our activities do not harm the environments we explore or the Earth itself. Human society and culture would be profoundly affected. The ability to travel to and colonize distant planets could lead to the development of new cultures and societies, each with their own unique characteristics and contributions to human civilization. Finally, the pursuit of faster-than-light travel would continue to drive scientific and technological innovation. It would push the boundaries of our current knowledge and capabilities, inspiring future generations to explore and discover the unknown. Current research into faster-than-light travel is primarily theoretical. Physicists are exploring the mathematical foundations of concepts like wormholes, warp drives, and tachyons, using the equations of general relativity and quantum mechanics. At institutions like CERN, high-energy particle collisions are being studied for anomalies that might suggest new physics. These experiments have not yet provided evidence for faster-than-light particles, but they continue to push the boundaries of our understanding. Astronomers are using advanced telescopes to search for gravitational lensing effects that could indicate the presence of cosmic strings. These one-dimensional defects in spacetime are hypothesized to have immense mass and tension, potentially facilitating faster-than-light travel. The study of gamma-ray bursts and other high-energy cosmic phenomena might offer clues. Researchers are looking for signs that these events produce or interact with particles that exceed the speed of light, which could point to new physics. Experiments with quantum entanglement are also relevant. While entanglement itself doesn't allow for faster-than-light communication, understanding this phenomenon better could lead to insights into non-local interactions that might be harnessed for superluminal travel. Physicists are investigating the Casimir effect as a potential source of negative energy. This quantum phenomenon creates a small force between two closely spaced metal plates, which could theoretically be scaled up to produce the exotic matter needed for warp drives. In the field of cosmology, the study of the universe's accelerated expansion due to dark energy might reveal new methods for manipulating space-time. Understanding dark energy could provide a key to achieving faster-than-light travel. Researchers are also exploring the possibility of creating artificial wormholes. These efforts involve theoretical work on how to stabilize such structures using exotic matter and ensuring they can remain open long enough for practical travel. Advanced simulations are playing a crucial role in this research. Supercomputers are used to model the complex interactions between particles and fields in extreme conditions, helping to test the feasibility of faster-than-light travel concepts. Experimentalists are attempting to detect any deviations from the expected speed of light in various mediums. These experiments test the limits of special relativity and look for any evidence that might suggest faster-than-light phenomena. Collaboration between disciplines is essential. Physicists, engineers, and cosmologists are working together to design experiments that can test these advanced theories and potentially provide the first hints of faster-than-light travel. Space missions equipped with sensitive detectors are being planned to gather data on cosmic phenomena that might relate to faster-than-light travel. These missions aim to observe high-energy events and gravitational waves with unprecedented precision. Observational evidence from black holes and neutron stars is also of interest. These extreme environments might produce conditions where faster-than-light effects could be detected, offering natural laboratories for testing these theories. Quantum computing advancements are aiding this research. These powerful tools allow for more complex simulations and data analysis, providing deeper insights into the potential mechanisms for faster-than-light travel. While no definitive evidence for faster-than-light travel has been found, the ongoing research continues to refine our understanding of physics. Each experiment and observation brings us closer to answering whether superluminal travel is possible, paving the way for future discoveries. Dark energy is a mysterious force driving the accelerated expansion of the universe. It makes up about 68% of the total energy content of the cosmos, yet its nature remains one of the biggest questions in modern physics. The discovery of dark energy came in the late 1990s. Observations of distant supernovae revealed that the universe's expansion is not slowing down, as previously thought, but is actually speeding up. This unexpected acceleration pointed to the presence of an unknown energy. One leading hypothesis is that dark energy is a property of space itself. According to this view, as space expands, more dark energy comes into existence, driving further expansion in a self-reinforcing cycle. The simplest explanation for dark energy is the cosmological constant, originally proposed by Albert Einstein. It represents a constant energy density filling space homogeneously. This model fits well with current observations but leaves many questions unanswered. Another possibility is that dark energy is a dynamic field, similar to the inflation field that drove the rapid expansion of the universe shortly after the Big Bang. This field would change over time, leading to varying effects on the rate of expansion. The concept of quintessence is one such dynamic model. It proposes that dark energy is a scalar field that evolves over time, affecting the universe's expansion in different ways depending on its state. Measuring the effects of dark energy involves observing the large-scale structure of the universe. By mapping the distribution of galaxies and clusters, scientists can infer how dark energy influences cosmic expansion over billions of years. The cosmic microwave background, CMB radiation, also provides critical insights. Tiny fluctuations in the CMB's temperature and polarization patterns carry information about the early universe and the role of dark energy in shaping its evolution. Dark energy affects the growth of cosmic structures. It counteracts gravitational attraction, slowing the formation of galaxies and clusters. This interplay influences the overall pattern of large-scale structures we observe today. Understanding dark energy is crucial for cosmology. It holds the key to the universe's ultimate fate. If dark energy continues to dominate, the universe will keep expanding at an accelerating rate, leading to a big freeze where galaxies move beyond each other's reach. Alternatively, if dark energy's properties change over time, it could lead to different scenarios, such as a big rip, where the acceleration becomes so extreme that it tears apart galaxies, stars, and even atoms. Studying dark energy also has implications for fundamental physics. It challenges our understanding of gravity, quantum field theory, and the nature of space-time. Solving the mystery of dark energy could lead to groundbreaking advancements in these areas. Experiments like the Dark Energy Survey, DS, and the upcoming Euclid mission aim to shed light on dark energy's properties. By collecting vast amounts of data on cosmic structures and expansion, these projects hope to unravel the nature of this enigmatic force. Theoretical physicists are also exploring new models and hypotheses. Some propose modifications to general relativity or entirely new theories of gravity to explain dark energy's effects. These ideas push the boundaries of our current understanding of the universe. Dark energy remains one of the most profound and exciting mysteries in cosmology. As we continue to refine our observations and theories, we move closer to uncovering the secrets of this force that shapes the cosmos on the grandest scales. The expansion of space itself offers intriguing possibilities for faster-than-light travel. Instead of moving through space, the idea is to manipulate space-time so that distant points come closer together. One concept is the Alcubierre warp drive, which involves contracting space in front of a spacecraft and expanding it behind. This creates a warp bubble, allowing the spacecraft to effectively travel faster than light without locally exceeding the speed of light. In this model, the spacecraft remains stationary within the warp bubble. The space-time around the bubble moves, which means the spacecraft doesn't violate the laws of special relativity. This manipulation of space-time could make interstellar travel feasible. To achieve this, the warp drive would require exotic matter with negative energy density. This matter would provide the necessary conditions to warp space-time in the desired manner. Finding or creating exotic matter is a significant challenge but crucial for this concept. Another idea involves using the natural expansion of the universe. If we could harness or enhance this expansion, we might create corridors of rapidly expanding space that shorten the distance between 2 points. This could function similarly to a cosmic highway. Expanding space could also be utilized in the concept of wormholes. These theoretical structures connect 2 distant points in space-time, effectively creating a shortcut. By stabilizing a wormhole, we could travel vast distances almost instantaneously. Wormholes, like warp drives, would require exotic matter to remain open and navigable. Ensuring the stability and safety of such a passage would be paramount, as the gravitational forces involved could be immense. The study of dark energy, which drives the accelerated expansion of the universe, might provide insights into how to manipulate space-time. Understanding and controlling dark energy could be key to developing faster-than-light travel technologies. Current research into the cosmic microwave background and the large-scale structure of the universe helps us understand how space-time behaves under different conditions. This knowledge is essential for any practical application of space-time manipulation. Quantum field theory also offers potential mechanisms for space-time manipulation. By exploring the interactions between quantum fields and gravity, physicists hope to discover new ways to control and utilize space-time. Advanced simulations and theoretical models are crucial in this field. They help scientists predict the behavior of warped space-time and identify the energy requirements and stability conditions for practical applications. Practical implementation of space-time manipulation would require breakthroughs in both theoretical physics and engineering. Developing the technology to create and control warp bubbles or wormholes is a monumental task that pushes the boundaries of current science. International collaboration and interdisciplinary research are vital. Physicists, engineers, cosmologists, and other scientists must work together to tackle the enormous challenges and complexities involved in faster-than-light travel. The implications of successfully manipulating space-time are profound. It would revolutionize space travel, allowing us to explore distant galaxies, discover new worlds, and perhaps even encounter other intelligent civilizations. As research progresses, each discovery brings us closer to understanding whether expanding space can indeed enable faster travel. The pursuit of this knowledge not only advances our scientific understanding, but also fuels our imagination and sense of possibility. Theoretical models and equations are essential for understanding and potentially achieving faster-than-light travel. These models often stem from the equations of general relativity, which describe how mass and energy warp space-time. One of the foundational equations in general relativity is the Einstein field equation. This equation relates the curvature of space-time to the energy and momentum of whatever matter and radiation are present. It forms the basis for understanding how gravity operates on a cosmic scale. The Alcubierre drive, a theoretical model for faster-than-light travel, is derived from solutions to the Einstein field equation. Miguel Alcubierre proposed a metric that allows for a warp bubble, which can move faster than light by contracting space in front of it and expanding space behind it. The Alcubierre metric involves complex calculations to describe the shape and behavior of the warp bubble. These calculations indicate the need for exotic matter with negative energy density to stabilize the bubble and enable faster-than-light travel. The energy-momentum tensor is a crucial component in these models. It describes the distribution and flow of energy and momentum in space-time. For a warp bubble, the tensor must include negative energy to achieve the desired space-time curvature. Wormholes, another theoretical model, are also solutions to the Einstein field equations. These equations suggest that a wormhole could connect two distant points in space-time, creating a shortcut that effectively allows faster-than-light travel. To keep a wormhole open, exotic matter with negative energy density is again required. The equations governing wormholes show that without such matter, the throat of the wormhole would collapse, preventing any travel through it. Quantum mechanics introduces additional equations and models that intersect with general relativity. The Schrödinger equation, for example, describes how quantum states evolve over time and can be used to understand the behavior of particles in warped space-time. In quantum field theory, the Casimir effect demonstrates how quantum fluctuations can create negative energy. This effect is described by equations that calculate the force between two closely spaced conductive plates, hinting at ways to produce exotic matter. Theoretical physicists also explore the concept of tachyons, hypothetical particles that travel faster than light. Equations governing tachyons involve imaginary mass and modifications to the standard energy-momentum relationship, presenting unique challenges and possibilities. String theory provides another framework for understanding faster-than-light travel. It proposes additional dimensions and fundamental strings whose vibrations determine particle properties. The equations of string theory offer potential insights into space-time manipulation. Loop quantum gravity is an alternative approach that attempts to quantize space-time itself. This theory uses equations that describe space-time as a network of discrete loops, potentially offering new ways to understand and manipulate the fabric of the universe. Advanced mathematical techniques, such as differential geometry and tensor calculus, are essential for working with these equations. These techniques allow physicists to describe and predict the behavior of complex systems involving space-time and energy. Continued research and refinement of these theoretical models and equations are crucial. Each step forward enhances our understanding of the fundamental laws of physics and brings us closer to the possibility of achieving faster-than-light travel. Interdisciplinary collaboration is vital in this field. Theoretical models must be supported by experimental evidence and practical engineering solutions, requiring a concerted effort across multiple scientific disciplines. The energy requirements for faster-than-light travel are immense. Theoretical models like the Alcubierre drive suggest that creating a warp bubble would require energy equivalent to the mass energy of entire planets or even stars. One potential source of this energy is antimatter. When matter and antimatter collide, they annihilate each other, releasing vast amounts of energy. Harnessing antimatter could provide the necessary power, but producing and storing antimatter in sufficient quantities is a significant challenge. Nuclear fusion is another potential energy source. Fusion reactions, which power the sun, release tremendous amounts of energy by fusing light atomic nuclei. Developing practical fusion reactors could provide a continuous and powerful energy supply. Dark energy, the mysterious force driving the accelerated expansion of the universe, is a tantalizing possibility. If we could understand and harness dark energy, it might offer a way to manipulate space-time and achieve faster-than-light travel. Zero-point energy is another speculative source. It represents the lowest possible energy state of a quantum system. Tapping into this pervasive background energy could provide a virtually limitless power source, although this remains highly theoretical. Exotic matter with negative energy density is essential for many faster-than-light travel concepts. Creating or discovering such matter is a significant hurdle, as it has properties vastly different from any known matter. Gravitational waves, ripples in space-time caused by massive objects, might be used for propulsion. Advanced technology could potentially capture and utilize these waves, though this idea is still in the early stages of theoretical exploration. Particle accelerators like those at CERN might provide insights into new forms of energy. By accelerating particles to near light speeds and observing the results, scientists hope to discover unknown particles or forces that could be harnessed for faster-than-light travel. Black holes could offer another energy source. The immense gravitational energy around black holes could potentially be converted into usable power. However, harnessing energy from black holes presents enormous technical and theoretical challenges. Solar sails use radiation pressure from stars to propel spacecraft. While not faster than light by themselves, they could be part of a hybrid system that combines multiple propulsion methods to achieve greater speeds. Quantum entanglement could revolutionize communication methods, allowing for instant data transfer across vast distances. While not an energy source, this mechanism is crucial for maintaining control and coordination of faster-than-light missions. Cosmic strings, if they exist, could provide a unique energy source. The immense tension and mass of cosmic strings might be harnessed for space travel, although their existence remains theoretical. Quark-gluon plasmas, hypothetical states of matter existing at extremely high temperatures and densities, could offer unprecedented power densities. These exotic forms of matter might be created and controlled for energy production. The Casimir effect, a quantum phenomenon where vacuum fluctuations produce measurable forces, might be scaled up to provide significant power for advanced space travel. This effect could be harnessed in ways we are just beginning to explore. Ultimately, the practical implementation of these energy sources requires significant advancements in both theoretical physics and engineering. Developing the technology to create and control the necessary conditions for faster-than-light travel is a monumental task. Faster-than-light travel refers to the hypothetical ability to move or communicate at speeds exceeding the speed of light in a vacuum, which is approximately 299,792 kilometers per second. The concept of faster-than-light travel challenges the foundations of modern physics, particularly Einstein's theory of relativity, which posits that nothing can travel faster than light without violating the laws of physics. One prominent theoretical framework exploring faster-than-light travel is the idea of warp drives, such as the Alcubierre drive. This concept involves manipulating space-time to create a warp bubble, which contracts space in front of it and expands space behind it, allowing for superluminal travel without locally breaking the speed of light. The theoretical basis for the Alcubierre drive comes from solutions to the Einstein field equations in general relativity. These solutions suggest that, under specific conditions involving exotic matter, space-time can be warped in such a way that faster-than-light travel becomes possible. Exotic matter with negative energy density is a crucial component of many faster-than-light travel theories. This type of matter has properties that are not observed in ordinary matter and is necessary to stabilize the warp bubble or keep a wormhole open. Wormholes, or Einstein-Rosen bridges, are another theoretical model for faster-than-light travel. These hypothetical structures connect two distant points in space-time, creating a shortcut that could allow for instantaneous travel between them. Quantum mechanics also offers potential insights into faster-than-light phenomena. Concepts such as quantum entanglement suggest that particles can affect each other instantaneously over vast distances, challenging classical notions of locality and causality. Theoretical physicists are investigating how quantum field theory and general relativity might intersect to allow for faster-than-light travel. These efforts involve complex mathematical models and simulations to explore the behavior of space-time under extreme conditions. String theory provides another framework for understanding faster-than-light travel. It posits that fundamental particles are one-dimensional strings vibrating at specific frequencies, and it introduces additional dimensions beyond the familiar four. These extra dimensions could offer new pathways for faster-than-light travel. Loop quantum gravity is an alternative approach that attempts to quantize space-time itself. This theory describes space-time as a network of discrete loops, potentially providing new insights into how the fabric of the universe can be manipulated for faster-than-light travel. The energy requirements for faster-than-light travel are a significant challenge. Theoretical models suggest that the amount of energy needed to create and sustain a warp bubble or stabilize a wormhole is enormous, far beyond our current technological capabilities. Experimental efforts to detect exotic matter or evidence of faster-than-light phenomena are ongoing. Particle accelerators, astronomical observations, and high-energy physics experiments are all part of the search for new physics that could make faster-than-light travel possible. The implications of faster-than-light travel extend beyond physics, affecting our understanding of time, causality, and the structure of the universe. It raises profound questions about the nature of reality and the limits of human exploration. Ethical and practical considerations are also important. If faster-than-light travel becomes possible, it will require new regulations, international agreements, and protocols to manage the potential risks and benefits associated with such a transformative technology. Interdisciplinary collaboration is essential for advancing the study of faster-than-light travel. Physicists, engineers, cosmologists, and other scientists must work together to address the theoretical, experimental, and practical challenges involved in making faster-than-light travel a reality. The role of exotic matter in faster-than-light travel theories is pivotal. It provides the negative energy density required to stabilize warp bubbles and wormholes, key components in many theoretical models. In the Alcubierre drive model, exotic matter allows for the creation of a warp bubble. This bubble contracts space-time in front of it and expands it behind, enabling the spacecraft to move faster than light without violating the laws of physics locally. Wormholes, another concept, require exotic matter to remain traversable. Without it, the throat of the wormhole would collapse, preventing any practical use for faster-than-light travel. Negative energy, a property of exotic matter, counteracts the positive energy that would naturally cause the warp bubble or wormhole to close. This delicate balance is crucial for maintaining the structure needed for superluminal travel. Quantum field theory suggests potential mechanisms for creating negative energy. The Casimir effect, for example, demonstrates how quantum fluctuations can produce measurable negative energy between two closely spaced plates. Theoretical physicists explore various models to understand how exotic matter might be produced or discovered. These models often involve high-energy particle collisions or interactions at quantum scales. In string theory, additional dimensions might harbor the exotic particles necessary for faster-than-light travel. These dimensions, beyond the familiar four, could provide the exotic matter needed for manipulating space-time. Loop quantum gravity offers another perspective, suggesting that space-time itself could have a granular structure. Manipulating this structure at a fundamental level might reveal new ways to achieve faster-than-light travel. Dark energy, which drives the accelerated expansion of the universe, is another area of interest. Understanding and harnessing this energy could provide the means to manipulate space-time on a cosmic scale. Researchers also look at high-energy astrophysical phenomena for clues. Events like gamma-ray bursts or interactions near black holes might produce conditions where exotic matter can form, offering insights into faster-than-light possibilities. The pursuit of exotic matter involves both theoretical and experimental efforts. Particle accelerators, like those at CERN, search for anomalies that might indicate the presence of unknown particles with the necessary properties. Advanced simulations help physicists predict how exotic matter might behave and interact with other particles. These simulations guide experimental designs and help refine theoretical models. Interdisciplinary collaboration is essential. Physicists, cosmologists, and engineers work together to explore the practicalities of producing and harnessing exotic matter for faster-than-light travel. The implications of successfully using exotic matter are profound. It would revolutionize our ability to explore the universe, potentially enabling human travel to distant galaxies and beyond. While the challenges are immense, the pursuit of exotic matter for faster-than-light travel represents one of the most exciting frontiers in modern physics. It holds the promise of transforming our understanding of the universe and our place within it. Creating and utilizing negative mass is a major focus in the pursuit of faster-than-light travel. One potential method involves exploiting the Casimir effect, where quantum fluctuations between two closely spaced plates create negative energy. Scaling this effect up could provide a source of negative mass. Another approach is through high-energy particle collisions in particle accelerators. These collisions could potentially produce exotic particles with negative mass properties. Scientists are continually refining these experiments to search for such anomalies. Quantum field theory offers various mechanisms for generating negative energy. By manipulating quantum fields, researchers hope to create conditions where negative mass can emerge, providing the necessary material for warp bubbles or wormholes. Some theorists suggest that negative mass might naturally occur in certain astrophysical phenomena. For example, the extreme conditions near black holes or neutron stars could produce regions of negative energy. Observing and understanding these environments could offer insights into creating negative mass. In string theory, additional dimensions might harbor exotic particles with negative mass. By exploring these hidden dimensions, physicists aim to discover or produce the negative mass required for faster-than-light travel. Researchers are also investigating the potential of dark energy. If dark energy, which drives the universe's accelerated expansion, can be harnessed, it might be possible to manipulate space-time in ways that create negative mass. Experimental efforts include developing advanced materials that exhibit properties similar to negative mass. These materials could interact with quantum fields in novel ways, potentially leading to the creation of negative energy densities. Another potential method involves using Bose-Einstein condensates, states of matter formed at extremely low temperatures. These condensates can exhibit unusual quantum properties, including behaviors that mimic negative mass. Theoretical models suggest that manipulating space-time at a fundamental level could generate negative mass. Techniques from loop quantum gravity, which describe space-time as a network of discrete loops, might offer new ways to achieve this. Gravitational waves, ripples in space-time caused by massive objects, might also be harnessed. By capturing and utilizing these waves, scientists could potentially create the conditions necessary for negative mass. The concept of vacuum energy, or zero-point energy, is another area of interest. Tapping into this pervasive background energy could provide a means to generate negative mass, although this remains highly speculative. Interdisciplinary collaboration is crucial in these efforts. Physicists, materials scientists, and engineers work together to explore the theoretical and practical aspects of creating and utilizing negative mass. Advanced simulations play a key role in this research. By modeling the behavior of exotic particles and quantum fields, scientists can predict how negative mass might be produced and utilized for faster-than-light travel. The potential applications of successfully creating negative mass are vast. It could enable the stabilization of warp bubbles and wormholes, making faster-than-light travel a reality, and opening up new frontiers for exploration and discovery. While the challenges are significant, the pursuit of negative mass is a vital part of the quest for faster-than-light travel. Each step forward brings us closer to understanding and harnessing the fundamental forces that shape our universe. The implications of faster-than-light travel for physics and cosmology are profound. Achieving superluminal speeds would challenge our current understanding of the fundamental laws of physics, particularly Einstein's theory of relativity. One major implication is the potential revision of our understanding of causality. Faster-than-light travel could lead to scenarios where cause and effect are reversed, requiring new theories to explain these phenomena without paradoxes. The discovery of negative mass or exotic matter would revolutionize particle physics. It would introduce entirely new categories of matter and energy, expanding the standard model and providing new insights into the nature of the universe. In cosmology, faster-than-light travel could change our understanding of the structure and evolution of the universe. It might allow us to explore regions of the cosmos that are currently beyond our reach, offering new data on the formation and behavior of galaxies, stars, and other celestial bodies. The ability to travel faster than light could also impact our theories about the Big Bang and the early universe. By observing distant cosmic events up close, we could gather evidence that either supports or refines existing models of cosmic inflation and the initial conditions of the universe. If faster-than-light travel is possible, it could provide practical means to test and validate theories of quantum gravity, string theory, and other advanced frameworks that seek to unify general relativity and quantum mechanics. The implications for dark matter and dark energy are significant. Faster-than-light travel technologies could enable direct observations and experiments that shed light on these mysterious components of the universe, potentially leading to breakthroughs in our understanding of their properties and roles. The concept of a multiverse could also be explored. If faster-than-light travel allows us to access different regions of space-time, it might provide evidence for or against the existence of multiple, parallel universes. In terms of technological advancements, the development of faster-than-light travel could lead to new materials and energy sources. These innovations would have wide-ranging applications beyond space travel, influencing fields such as energy production, transportation, and communications. The pursuit of faster-than-light travel will likely drive advancements in computational physics and simulation techniques. These tools are essential for modeling complex systems and predicting the behavior of exotic matter and warped space-time. Ethical and philosophical questions will also arise. The ability to travel faster than light could fundamentally alter our perspective on space, time, and existence, prompting new debates about humanity's place in the universe and our responsibilities as explorers. The societal impact of faster-than-light travel could be immense. It could lead to the development of new civilizations on distant planets, with their own cultures, laws, and innovations, ultimately enriching the diversity and resilience of human society. Educational systems would need to adapt to these new frontiers. Training the next generation of scientists, engineers, and explorers to understand and utilize faster-than-light technologies will be crucial for continued progress and innovation. Collaboration between nations and international organizations will be essential. The development and regulation of faster-than-light travel will require global cooperation to ensure that its benefits are shared equitably and that potential risks are managed responsibly. In summary, the implications of faster-than-light travel extend far beyond the realm of physics and cosmology. They touch on every aspect of human knowledge and society, offering unprecedented opportunities for discovery, innovation, and growth. Throughout our exploration of faster-than-light travel, we've delved into several key theories and concepts that challenge our current understanding of physics and open new possibilities for interstellar exploration. The concept of warp drives, particularly the Alcubierre drive, proposes creating a warp bubble that contracts space-time in front of a spacecraft and expands it behind, allowing for superluminal travel without locally exceeding the speed of light. Wormholes, or Einstein-Rosen bridges, are theoretical passages through space-time that could connect distant points, effectively creating shortcuts that enable faster-than-light travel. These structures require exotic matter to remain stable and traversable. Exotic matter, with its negative energy density, is a critical component in many faster-than-light travel theories. It provides the necessary conditions to stabilize warp bubbles and keep wormholes open, despite its elusive and theoretical nature. Quantum mechanics introduces phenomena like quantum entanglement and the Casimir effect, which suggest potential mechanisms for faster-than-light communication and the creation of negative energy, respectively. These quantum principles challenge classical notions of locality and causality. String theory, which posits additional dimensions and fundamental strings, offers a framework for understanding how faster-than-light travel might be possible by manipulating these extra dimensions or finding exotic particles within them. Loop quantum gravity, an alternative approach to quantizing spacetime, suggests that spacetime is composed of discrete loops. This theory might provide new insights into how the fabric of the universe can be manipulated for faster-than-light travel. Tachyons, hypothetical particles that travel faster than light, present unique theoretical challenges and possibilities. Their existence would require a revision of the standard energy-momentum relationship and introduce new categories of particles. The study of dark energy, which drives the accelerated expansion of the universe, might reveal ways to manipulate space-time on a cosmic scale. Understanding this mysterious force could be key to developing faster-than-light travel technologies. High-energy astrophysical phenomena such as gamma-ray bursts and interactions near black holes might produce conditions conducive to the formation of exotic matter. Observing these events could provide clues to achieving faster-than-light travel. Advanced simulations and mathematical models are crucial for exploring these concepts. They help predict the behavior of exotic matter and warped space-time, guiding experimental designs and refining theoretical models. Particle accelerators, like those at CERN, are instrumental in the search for new physics that could enable faster-than-light travel. By observing high-energy collisions, scientists hope to discover unknown particles or forces. The pursuit of faster-than-light travel has profound implications for our understanding of the universe, from the structure and evolution of the cosmos to the fundamental laws of physics. It challenges our current theories and drives the search for new ones. The potential technological advancements from this research could revolutionize multiple fields, including energy production, transportation, and communications. These innovations would have far-reaching impacts beyond space exploration. Ethical and philosophical questions will arise as we approach the possibility of faster-than-light travel. These include considerations of humanity's role as explorers, our responsibilities to other potential civilizations, and the management of new technologies. The journey to achieve faster-than-light travel is complex and challenging, requiring interdisciplinary collaboration and global cooperation. As we continue to explore these frontiers, we push the boundaries of what is possible and expand our horizons, both scientifically and culturally. The current state of faster-than-light research is largely theoretical, driven by advances in our understanding of physics and cosmology. Scientists are exploring the mathematical foundations of concepts like warp drives, wormholes, and exotic matter. At research institutions around the world, particle accelerators are pushing the boundaries of high-energy physics. Experiments at facilities like CERN aim to discover new particles and forces that might make faster-than-light travel feasible. Theoretical physicists are developing models to explain how space-time could be manipulated. These models often involve complex calculations based on general relativity and quantum mechanics, seeking to find consistent solutions that allow for superluminal travel. In the realm of quantum mechanics, researchers are investigating phenomena like quantum entanglement and the Casimir effect. These studies aim to understand how quantum principles might enable faster-than-light communication or create the negative energy needed for warp bubbles. Astrophysicists are observing high-energy cosmic events for indirect evidence of faster-than-light effects. Gamma-ray bursts, black hole interactions, and other extreme phenomena might provide clues to the existence of exotic matter or other necessary conditions. Dark energy remains one of the most mysterious aspects of the universe. Researchers are working to understand its properties and potential applications for space-time manipulation, which could be crucial for achieving faster-than-light travel. Advanced simulations are playing a crucial role in this research. Supercomputers model the behavior of space-time under extreme conditions, helping scientists predict the feasibility and stability of warp drives and wormholes. Collaboration between disciplines is essential. Physicists, engineers, cosmologists, and computer scientists are working together to explore the theoretical and practical challenges of faster-than-light travel. The search for exotic matter continues. Efforts to detect particles with negative energy density are ongoing, with experimental setups designed to observe rare quantum effects that might indicate their presence. Innovative propulsion concepts, such as the Alcubierre drive, are being refined. These models require a deep understanding of general relativity and the ability to manipulate space-time, making them a focus of cutting-edge theoretical research. Quantum field theory is being applied to explore new mechanisms for faster-than-light travel. By understanding how quantum fields interact with gravity, researchers hope to uncover new ways to manipulate space-time. Space missions equipped with advanced detectors are planned to gather data on cosmic phenomena. These missions aim to observe high-energy events and gravitational waves with unprecedented precision, potentially revealing new insights. Theoretical breakthroughs are essential for guiding experimental efforts. Each new discovery in the realms of quantum mechanics, general relativity, or cosmology helps refine our understanding and brings us closer to practical applications. International collaboration is crucial for advancing this field. Scientists from around the world share data, resources, and expertise, working together to tackle the immense challenges of faster-than-light research. While faster-than-light travel remains speculative, the ongoing research continues to push the boundaries of our knowledge. Each step forward not only brings us closer to realizing the dream of superluminal travel, but also deepens our understanding of the universe and the fundamental laws that govern it. Potential future breakthroughs in faster-than-light travel could revolutionize our understanding of physics and open new frontiers in space exploration. One of the most exciting prospects is the discovery or creation of exotic matter with negative energy density, which is crucial for stabilizing warp bubbles and wormholes. Advancements in particle physics might reveal new particles or forces that enable faster-than-light travel. Discoveries at high-energy particle accelerators could provide the missing pieces needed to make superluminal speeds a reality. The development of practical fusion reactors could supply the immense energy required for faster-than-light propulsion. Fusion technology is progressing, and achieving a sustainable fusion reaction would be a monumental step forward. Understanding and harnessing dark energy could lead to groundbreaking methods for manipulating space-time. If we can control this mysterious force, it might provide the key to developing faster-than-light travel technologies. Breakthroughs in quantum computing could enable more sophisticated simulations and models of space-time manipulation. These advanced computational tools could help scientists design practical systems for superluminal travel. The discovery of natural wormholes or evidence of their existence would be a significant breakthrough. Observing these structures in the cosmos could validate theoretical models and provide insights into how to create and stabilize them artificially. Innovations in material science could lead to the development of new materials capable of withstanding the extreme conditions of faster-than-light travel. These materials would be essential for constructing warp drives and other advanced propulsion systems. The detection of tachyons or other faster-than-light particles would revolutionize physics. Confirming their existence would challenge current theories and provide a new direction for research into superluminal travel. Progress in our understanding of quantum entanglement could lead to practical applications for instant communication across vast distances. This would be crucial for coordinating interstellar missions and maintaining contact with distant explorers. The development of new theories that unify general relativity and quantum mechanics could provide a more comprehensive framework for faster-than-light travel. These theories might reveal new aspects of space-time that we can manipulate. Discoveries in cosmology, such as the nature of the early universe or the behavior of black holes, could provide clues about how to achieve faster-than-light travel. Observing these extreme environments might offer practical insights. Collaborative international projects could accelerate progress in this field. By pooling resources and expertise, nations can work together to tackle the immense challenges of developing faster-than-light technology. Innovative propulsion systems that combine multiple advanced concepts might emerge. Hybrid systems that utilize both warp drives and other high-speed propulsion methods could offer practical solutions for interstellar travel. Public and private investment in space research could drive significant advancements. Increased funding and interest in exploring faster-than-light travel would support the development of new technologies and experimental approaches. Ultimately, each breakthrough, whether theoretical or experimental, brings us closer to the dream of faster-than-light travel. The ongoing pursuit of these discoveries not only expands our knowledge, but also fuels our imagination and aspirations for the future. Challenges and ethical considerations in the pursuit of faster-than-light travel are significant and multifaceted. One major challenge is the immense energy requirements. Developing technologies capable of generating and sustaining the required energy levels is a daunting task. Creating and stabilizing exotic matter is another critical hurdle. Exotic matter, necessary for concepts like warp drives and wormholes, has properties that are not yet understood or observed, making its production a significant scientific challenge. Theoretical models often predict instability in faster-than-light travel methods. Ensuring that warp bubbles or wormholes remain stable during travel without collapsing or causing harmful side effects is crucial for practical application. Navigational challenges at faster-than-light speeds are substantial. Traditional navigation systems may not function correctly under these conditions, requiring new technologies to ensure precise control and safety. The potential impact on human physiology is also a concern. The extreme conditions associated with faster-than-light travel could pose risks to human health, necessitating extensive research into protective measures and long-term effects. Communication across vast distances during faster-than-light travel presents another challenge. Developing methods for reliable and instant communication with spacecraft traveling at superluminal speeds is essential for mission coordination and safety. The potential for time paradoxes and violations of causality raises profound theoretical and ethical questions. Faster-than-light travel could lead to scenarios where cause and effect are reversed, challenging our understanding of time and requiring new philosophical frameworks. The economic cost of developing faster-than-light technologies is significant. Large-scale investment from both public and private sectors will be needed, raising questions about the equitable distribution of resources and benefits. The potential militarization of faster-than-light technology is a serious ethical concern. Ensuring that such powerful technology is used responsibly and not for destructive purposes will require robust international regulations and agreements. Environmental impacts must also be considered. Manipulating space-time on such a scale could have unforeseen consequences for both space environments and planetary ecosystems. Thorough environmental assessments and safeguards will be necessary. The exploration and potential colonization of distant worlds raise ethical questions about the treatment of any discovered extraterrestrial life. Establishing guidelines for respectful and responsible interaction with alien ecosystems is crucial. Equitable access to faster-than-light technology is another ethical issue. Ensuring that the benefits of this technology are shared globally and not monopolized by a few nations or corporations will be essential for fostering global cooperation and equity. The societal implications of faster-than-light travel are profound. It could lead to the development of new cultures and societies in distant star systems, necessitating thoughtful consideration of how these new societies will relate to Earth and each other. Public perception and acceptance of faster-than-light travel will influence its development and implementation. Engaging with the public, addressing concerns and fostering a sense of shared exploration and discovery will be important. Ultimately, the pursuit of faster-than-light travel must balance ambition with responsibility. By addressing the challenges and ethical considerations thoughtfully and collaboratively, humanity can strive to achieve this extraordinary goal in a way that benefits all and safeguards the future. In this video, we explored the fascinating and complex world of faster-than-light travel, delving into the theoretical concepts and scientific principles that challenge our current understanding of physics. We began with an overview of the speed of light, setting the stage for the immense challenges and exciting possibilities that faster-than-light travel presents. We discussed the key theories, including warp drives, wormholes, and tachyons, and how these concepts could potentially allow for superluminal travel. The role of exotic matter and negative energy density was highlighted as a critical component in stabilizing these theoretical constructs and making faster-than-light travel feasible. Our journey took us through the realms of quantum mechanics and the Casimir effect, examining how quantum principles might provide mechanisms for faster-than-light communication and space-time manipulation. We also explored the implications of dark energy and the accelerating expansion of the universe, considering how these cosmic forces might be harnessed for interstellar travel. We touched on the challenges and ethical considerations that come with the pursuit of faster-than-light travel. From the immense energy requirements and the need for exotic matter to the potential impacts on human physiology and environmental concerns, these are significant hurdles that must be thoughtfully addressed. Throughout our exploration, we considered the potential breakthroughs that could revolutionize our understanding of physics and open new frontiers in space exploration. From advancements in particle physics and fusion technology to the discovery of natural wormholes and innovations in material science, the future holds many exciting possibilities. We also discussed the current state of research, emphasizing the importance of interdisciplinary collaboration and international cooperation. The journey to achieve faster-than-light travel requires the combined efforts of physicists, engineers, cosmologists, and other scientists, as well as significant investment from both public and private sectors. If you enjoyed this deep dive into the world of faster-than-light travel, please like and subscribe to our channel. Your support helps us continue to bring you informative and engaging content. Be sure to check out the rest of our videos, where we explore other fascinating topics in science, technology, and space exploration. Thank you for watching, and stay curious.